I hope you can hear me well. And good morning or good afternoon or good evening, wherever you are. Welcome and thank you for joining us in this second data science summer school organized by Hertie School Data Science Lab. And this year summer school is organized and funded by the Hertie School, and we're really grateful for their support. We wanted to note a couple of organizational and technical details. First, as you might have noticed already, if you're with us for this fourth workshop, we start with the introductory courses and programming and some mathematical foundation essentials for the success of the data scientists. We already had some workshops on R and Python, and now we're proceeding with the mathematical foundations. If you missed our previous workshops, you can see it on our webpage and check out all the materials. And thanks for joining and can keep being with us in this kind of series of the events. And this part of the mathematical foundations and the programming part is part of the technical preparations for the Master of Data Science for Public Policy program that we have here in Hertie. But obviously, as you already noticed, it is open for everyone. So we're really excited to see all of you and welcome all of you today. So now a little bit about technical details. If you have been at the previous workshops with us, or it's going to be a repetition for you, but if you're here for the first time, I'm just going to repeat that if you're on Zoom with us, you might have noticed that you're muted and your videos are off upon entry. We will ask you to keep it like that. And if you do have a question, please put it in the chat. We're going to be monitoring the chat and trying to address all of your questions, either by responding in the chat or bringing it up to the instructor. Or if you do want to ask the question out loud, please raise a hand and we will let you speak whenever there's going to be a moment to ask the question. If you're joining us on YouTube in this parallel stream session, welcome as well. And we just want to ask you to put your questions in the live comments box of the YouTube, and we will try to either address your question right away in this comment section, or we will bring up your question to the instructor, just like asking it out loud. The final thing that I want to note is this Zoom session is being recorded. And if you do unmute yourself in Zoom and put your video on, you're automatically agreeing to being recorded and your voice and your image being recorded as well. Thanks in advance for following these rules. And now I just want to welcome everyone in this fourth workshop session. And today we have linear algebra for data science. And let me introduce you Dr. Lewin Stein, who is going to be our instructor for today. Lewin is currently a supercomputing and computational fluid dynamics consultant at the Zeus Institute in Berlin. He has a PhD in physical engineering from TU Berlin, and he has years of experience with software development with a focus on computational fluid dynamics and acoustics. And without further ado, Lewin, the floor is yours. You can share your screen now. You already did. And welcome everyone, and I hope you guys will have fun and good luck.
Thanks so much, Olga, for this awesome introduction. So I start right away. Welcome you to my 4-hour workshop on basics in linear algebra. When I go to the first slide. So in Hertie School, there is this master course of data science. And in this summer school is, on the one hand, preparation for those people who are attending this master in data science, but who don't know many linear algebra. But of course, generally, I guess if you're attending the summer school, you already have the possibility to see some lectures over the whole program of this master. And especially topics like machine learning, deep learning, are probably maybe the goal of some of yours. But yeah, there are many different things. And in order to do this like in a proper manner and to really understand what is going on under the hood, like this analysis and linear algebra are the biggest, like, let's say, classic math lectures most universities offer, and which are really like the foundation you need to bring. And with those two basic foundations, I can also have like maybe the laser pointer here, more visible. You have a good foundation both for programming, which is also part of summer school. Like I think you have an offer to listen to an R course and a Python course. And yeah, all the theory, which is covered in this mathematics for data science lecture, leading to the mechanics of machine learning. They all both profit basically from analysis and linear algebra. And linear algebra is the topic now I'm going to focus on. And the object or content of today are to introduce like the most basic objects of linear algebra, which are scalars, which are simple numbers, vectors, which is a 1D line of numbers, matrices, which are basically 2D arrangements, rectangular arrangement of numbers, and then we have tensors, which is just a generalization of an n-dimensionally collection of numbers, but that's not the focus today. And then we somehow talk about how these objects can be related to each other. There's something like a vector space where these objects live in. Then we have some relation between these objects, which we call linear independence or dependence, either or. And then you can also like have a span or a basis out of vectors. We learn how to interact and operate on those objects. So there are basic things typically appear in algebra and also then in dependent subjects like machine learning. So you need to know what is a determinant, a matrix multiplication, which is different from a scalar one. And then there are other operations we go into detail soon. And maybe if we have still time, I'm going to talk about eigensystems. So that's for the content part. And for sure, I cannot cover everything. I hope you tell me where to focus by giving questions in the chat or just asking them. But yeah, in case something is too fast, that's also natural. You can maybe just read up my slides again, since they will be uploaded, as well as my recording. So yeah, I recommend you to go to the slides again if you missed something. And yeah, as literature recommendations, there's some ebooks here in the beginning. I think they're also on the webpage of Hertie School. And then if you want to try out something yourself and you do not have a installation of some programming language already running, then there's a nice web interface by Wolfram Alpha where you can basically do all matrix operations and vector modifications you see today directly online and see how it's doing. And I found some nice visualization on YouTube, which is made by some guy, unfortunately under some license. So we cannot upload the video content on the slides, but I post here all the links of the video content. So if you watch this at a later time, you simply can follow this link to see the visualizations of the things you learned today. So with this, we start with the content, the basic concepts. And I jump into the cold water, let's say. So I want to motivate first why you need it. And here the first message is you can do something with the matrix. It acts like as an operator on a vector. So what is a matrix and the vector? The vector is a 1D line of numbers. You can see it here. There are two ones. And in case you have like a 2D rectangular construct of numbers, like these two here, then we call this a matrix. So this is basically just a 2D arrangement of numbers. And this now is already like the answer to one of the questions in the initial poll. So I was providing you a vector, and now you already start with some geometric interpretation. Namely, the vector can be represented like on a coordinate system with an x-axis and a y-axis. And then you can interpret this vector here as the ending point of an arrow. So the 1, 1 corresponds to the ending point. So this is the 1 in x direction here, which is the first component of our vector. And then there's the second component of our vector, which corresponds to the second dimension in y direction of our vector. So 1, 1 in both directions of x and y in this naive coordinate systems will give you exactly this vector. And in linear algebra, you can always draw the vectors like starting from 0, 0, and the vector content shows you where the arrow ends. So all vectors for now always start from 0. And the question was, yeah, what is happening if you rotate it counterclockwise by 90 degrees around the origin? This is indicated by the arrow here, and the resulting arrow then is at -1, 1. So this is the resulting vector I was asking you, and I think most people got it right. The matrix here is somehow acting on this vector, and we go into detail how this works. So far, I just wanted to point you out that like this matrix is actually doing the job of the rotation. So we call this operation a linear transformation. So in linear algebra, all matrices are doing always linear transformations. So this transformation you can simply interpret in this case as rotation of a vector. And the other typical operation, what you could do is you could stretch the length of the vector. You can also do both. You could rotate and stretch the length. So if you want to maybe add a stretching as well, you could add a 2. You multiply the whole matrix by 2, or you could also just multiply the whole thing here by 2. And as you can imagine, if you multiply the vector by 2, it has double the length. So in case you multiply the matrix by 2, then the matrix has -2 and 2 here, and then it will do both rotation and stretching. So this is like a common thing in linear algebra. You have like linear operations done by matrices. Okay, so next I want to go to the final goal, maybe of some of yours, which is machine learning or maybe even then deep learning. So what we see here is again like a vector and a matrix, and the matrix here is basically somehow combining the vector entries in some manner, and this combination then is calculated together and gives another entry of another vector like one level below. And basically in the most complex case, a subsequent or following vector always depends on all numbers in the vector before. And what this example is doing here is a classification problem. So I assume here you already got a neural network trained, which is basically can be represented by a combination of matrices. And what this neural network can do is somehow if you plug in a letter which is written and you digitalize this letter, this should be a small a, then this algorithm tells you what is actually the letter. So of course the computer does know that this is an A, but inside the neural network somehow this information is stored, and then the output is also a vector, and in most cases. Of course, you can also do more complex stuff, but for now it's sufficient. Tells you, okay, these are all possible options I want to look for. So you can train the network only to look for smaller case letters, or you can tell the network to only look for Greek letters, or in this case, I look for the letters A, B, C, D, E, and then I start for capital letters A, B, C, D, E. And let's assume this network is like quite good, or let's say okay, and then it tells you, okay, the highest likelihood is that this A is actually A is 60%, but okay, it could be also a small d. Small d is looking quite similar. This also has a quite big percentage. So the main point here is that all the mass can be basically represented by matrices. And yeah, maybe I can just tell you the sub-steps of this model here. So the first part is just to have the JPEG converted to a bitmap. So a bitmap basically, here's a grayscale bitmaps. The value 250 corresponds to a white color, and 0 corresponds to black color. And in the beginning, you have a lot of white. If you look at this picture, so in the digital number representation of your image in the computer, you first have here white, 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 and then some way later in this vector, you maybe get some black. So all pixels in this picture here are put into one long line, which is our vector, our one-dimensional vector. And what you first need to do in machine learning usually is to clean the data. So in case your picture has like a lot of white around it, a lot of big white margins, you need somehow to crop it, and then you can define a matrix operation which is doing this cropping. So the matrix is doing the job of cropping, and then you arrive at another vector, which has a smaller dimension, which is great because then this takes less storage and it's easier to process further. And you see that here the numbers are actually making more sense because those numbers here have, yeah, some gray values going slowly to black. And next thing you usually do, you need to define some smart features. Meaning, for example, you could ask to calculate the height of this letter or the width. And based on those characteristic features of the letter, you can then make a decision, okay, if I have this feature really big and this feature really small, then it possibly is an I, or something like this. But yeah, this is more the content of a machine learning lecture. This is like a teaser to get you excited. I already see some questions regarding principal component analysis. Maybe I come back to this if we make it all the way to the eigenvalue and eigensystem in the end of this lecture. Let me read the questions. I'm at the moment doing some principal component analysis, and the probability for a match sounds very much like the variance. So, yeah, this question now is really deep into the topic of machine learning. So I think, yes, the variance and the probabilities in percentage is exactly the same. So this is just one way to display the output of such a learning model, exactly. But yeah, I give some more details about principal component analysis, at least at the very end, if we make it through. So let's see. Another example. So I myself was introduced like as a CFDler, meaning computational fluid dynamics. So I studied how gases and fluid moves, like during my master's and also during my PhD. So this picture is actually coming from my master thesis. And here you see some, vortices. And this is actually like a so-called vorticity. It's the measure how fast particles are rotating. And here are two colors. So the red colors means particles in this part are rotating counterclockwise, and the blue particles here below are rotating clockwise. So you have here basically now, some fluid moving. So it looks like a kind of mushroom, and this mushroom like moves to the right and becomes more complex while doing so. So this is the time. So some 0.1 seconds, which is elapsed here between those two pictures. And what I point out here, that basically if you have like fluid dynamic equations, you can linearize them, and actually you need to do it in order to calculate those fluid equations with a computer. And then if you're done linearizing, in the very end, you have really just a simple matrix with numbers inside. And these numbers now tell you, if you plug in the fluid state at an early time, so let's say at this 0.1 seconds at an old state. So what you need to plug in, you need to describe the full physical state. And in this case, you need to tell what is the density of the fluid, what is the local velocity, and what is the local pressure for each point, like in this picture. So these numbers here, they represent different geometric positions in this picture. And then the matrix tell you how this fluid will be at a later point in time. So this now is quite a big jump in time. Actually, the trick to really do it as a linear transformation is to do a tiny time step. So this time step is way too huge. And why I'm telling you this, actually in linear algebra, as I told you, you only can like shear, stretch, and rotate things, but you cannot create new geometry. So if you compare these pictures, you see that they're actually like new objects, like new tiny worlds appearing. So this is not possible with a single linear transformation. Well, the trick is to do like one tiny time step with a linear transformation, and then you actually need to update the content of the matrix and then do another tiny time step. So actually between those pictures, I think there are like thousands of tiny linear time steps. And all these linear time steps together actually can do something more complex, and like this. So just as a point. So now then I want to start with from scratch, telling you the idea about the basic objects. First, here we have the vector. As I told you, it's a one-dimensional line of numbers. Each number is a scalar value. And today we only work with real numbers. So there's no complex number, just the numbers, let's say, you know, from school. Or let's say from basic school. And yeah, you plug in all these numbers together, and then you define this vector. And there are different notation variants. So this somehow makes it tricky if you jump between literature. Everybody has his own style. So most common is that you use lowercase. So all vectors typically have lowercase. And some people like to make vectors with bold font. So in the beginning of my slides, I like to differentiate between a scalar, which is a single value, and a vector, and the vector is then bold font in contrast to a single scalar value. So indicating something bold contains more. But later in the slides, which are not all by me, but also made by the Professor Lynn Kark of Hertie School, and there are more vectors coming out without bold font. So I stay tuned for that. I remind you that there's not always bold font. And other variants are a tiny arrow. So we learned already that you can visualize a vector like in 2 dimensions. You have the x and y coordinates, and then you can draw simply an arrow here. So this is also like a nice reminder of this geometric interpretation of a vector. And some people also do an underbar of a vector. So all this can be a vector, and yeah, regarding of context, people use one of these notations. So now my presentation is slightly hanging. I'll just do it with my keyboard. Okay, this is just one example of a stupid vector with zeros and one position I, which is the ith entry of this row of numbers. The ith entry has a 1. And in machine learning, apparently, I'm no expert in machine learning, but yeah, you call that one hot vector. Maybe this will come up for you. So next object is a matrix. It's a rectangular arrangement of numbers. It can be a square, but most generally it's a rectangle. And yeah, we have here the height of this, or the number of numbers in the vertical are n, and the number of numbers in the horizontal are n. So this m and n tells you how many numbers are there in both dimensions. And again, in contrast to a vector, a matrix is written with a capital letter, not with a small case letter. Sometimes people, again, like to use bold font, and sometimes people like to use a double underbar to indicate that we are working with a matrix. And another thing is, if we just want to pick one value of a matrix, let's say component IY, then we can write it like this way. Actually, this is a little bit misleading because this is a scalar value. If you pick a single value out of a matrix C, this is a scalar. So actually, this could be also written with small case now, like small a, I, j. But yeah, sometimes if you want to point out that this scalar value comes out from a big matrix, then this matrix origin leads to this still uppercase notation, even though we are just talking about a single value, a scalar one of a matrix. So yeah, notation is always a little bit tricky. And I give you some examples for matrices. So this is a square matrix. So both in the horizontal and the vertical direction, we have n elements. Then we can have like a more simple case of a matrix, which actually appears quite often, which is a diagonal matrix, which only has entries in the diagonal, and all other entries are 0. And an even more specialized case is identity matrix, where all the diagonal entries are 1. So now I make a short excursion to programming, since I heard that plenty of you are mainly interested how to implement like mathematic problems. So depending on oh no, let's start from scratch. In computer storage, there is no like real 2D arrangement, but everything in a computer basically is a single one-dimensional line. So for a vector, this is great. So the vector directly can correspond to this one-dimensional storage line of a computer. But with a matrix C, you have somehow two possibilities how to save or store a matrix into your storage or into the cache. And one way to do it, like the human or the Western human is reading, and I have to say, so this zigzag is like the first row first is stored in storage, and after this is done, you start with the second row, and then you repeat this zigzag pattern. So why this is important? If some elements are close in storage, you can access them the fastest. So the programming languages like NumPy, which is a linear algebra package of Python, or C++, they store elements exactly in this pattern, which we call row major. So row goes first in the storage, meaning if you pick neighbored elements in a row, you can pick those really fast after each other. While if you pick elements from different rows directly behind each other, this takes more time because there is a larger distance in memory. And one implication of this is if you have a row major programming language, then you have a matrix object here, matrix A with two components ij. You can access the rows the fastest, and the index which is running through the row is the second one. So the second index is changing in the row. Here's a 1, then a 2, and it goes all the way to n. It's the second index, meaning the second index j is the fastest, meaning the innermost loop, if you do some operations. So this is like a stupid operation, just placing a 0 inside this entry. But the fastest row should be the innermost. And this is exactly here the case. So j is the fastest index, it's the second index, and this is the innermost loop, which is the changing most frequently, and the outermost loop is changing less frequency, and therefore should be the first index. And now the opposite is true for so-called column major ordering. So you can guess column major means you first read all the columns entries, and then you jump to the next column. And those storing format is used, for example, by R, Julia, MATLAB, and Fortran. So already in, I think, the summer school, you have the chance like either to pick Python or R. So already here you have options how to access elements in matrix more performant or less performant. Okay, so back to math.
I'm so sorry. There is like a hand. Wen wants to ask a question. So Wen, if you want to go ahead and just ask right now, maybe.
Yes, cool.
Okay, maybe we can like go ahead and then I'll ask to put the question in the chat. Sorry.
Okay, yeah, no worries. Maybe I can also, I only have the chat window open. Maybe I can have the whole Zoom thing open, but somehow I didn't saw the hand, but it doesn't matter. Maybe I need the list of participants.
No worries, I can
okay.
do it.
Cool, fine. Thank you. So then I go back to the basic math, and I introduce the first operation you can do with a matrix C, namely you can flip column and rows. So this is called the transpose operation. So we have a matrix C A with real entries. The dimension of the matrix is m times n. And now we want to calculate a so-called transpose. This is noted by a to the power of t, which tells you that you want to calculate the transpose. And one way to define it, that if you access the element ij of the transpose matrix, it's the same as assessing the element ji, which is the flipped order of the original matrix. So what this basically does is really just flipping column and rows. And for example, we can apply this operation to a vector. So we have most often vectors are columns always, but sometimes we also need a vector in a row shape. And to get this vector in a row shape, you can calculate the transpose of a vector in a column shape, and then you get the vector like in a row shape. And similar thing with the matrix C. Either you can flip columns and rows, or you can also imagine this transpose operation geometrically, meaning you have the diagonal axis as mirror axis, and then basically you flip all numbers around this mirror axis. So the upper 2 here goes to the lower left and vice versa. So there are some properties. If you do this transpose operation twice, you end up with the original matrix C. So this you can imagine this easily, like if you flip columns and rows once, and then you flip them again, you end up with the original state. Then it doesn't matter if you add up 2 matrices and then do the transpose, or if you transpose the matrices individually and then do the adding. by the way, if you add up two matrices, you do this element-wise. So the first element of the first matrices is added up to the first element of the second matrices, and so on and so forth for each element individually. There is also something called like a matrix multiplication. So this is actually following way later in my slides, but I already give you here some information regarding the transpose operation. So if you want to do the transpose of the product of two matrices, you actually need to take care and invert the order of the matrices to do it individually on both matrices. So this becomes clear later, but yeah, just to make sure that it's not similar to the addition, but the matrix multiplication, you need to also flip the order if you want to apply the transpose operation on the matrix individually. Then some matrices have some special properties, namely they are symmetric, especially then when A is equal to its transpose. So if the transpose looks the same as the original matrix, then we call this matrix symmetric. And then there's also the counterpart, the antisymmetric matrix is if we do the transpose of a matrix and then it looks the same as the original matrix, but with a minus sign. So actually, this is the case here of my tiny matrix example here. So either we could do the transpose operation, like with a flipping, or we could simply multiply a minus in front of the original matrix, and then we end up, if we multiply the minus to all elements, so always you apply operations element-wise to all entries, we end up exactly with the same. So this is the definition of an antisymmetric matrix. Okay, just for like generality, I want to mention that there are like higher dimensional objects. So you can extend a matrix to also 3 dimensions. So you arrange numbers also in the third dimensions. And actually you can do this with any dimensions. And a tensor basically now is an object which can have any dimensions to store numbers inside. But yeah, in this lecture, we stick to 1 and 2 dimensional arrangement of numbers. So we stick to simple vector and matrices. So now I want to talk about how vectors are related to each other and which spaces they live in. So basically in math, there is a lot of theory of the spaces where vectors live in. And yeah, we basically just use their theoretical foundations, and one is a vector space, or this vector space is sometimes also called linear space. So the linear space is basically the space which holds all the vectors we are talking about in linear algebra. And yeah, the linear space can have a certain dimension, and this dimension of the linear space corresponds to the dimension of the vector. So if a vector has n entries, then the vector space corresponding to this vector has the dimension n. And inside this vector space, which is denoted by this like variant of a v, and there are 2 operations defined how vectors can interact with each other, and those are belonging like per definition to the space, and this is addition and scaling. So either you can like do addition of 2 vectors and end up with a third vector, and what is always the case is that the resulting vector lives inside the same vector space as before. So it has the same dimension also as before. You can look here at an example how this can be visualized in 2 dimensions. Here you have like the 2 vectors, a red one and a blue one, and the addition basically now adds up element-wise all components. So you add up the first entry of the blue vector with the first entry of the red vector, and so on till the very last entry n. And then you end up with the resulting vector, which is here the black vector. And the black vector is somehow the diagonal of this ellipse, not ellipse, but parallelepiped, or this Raute-like shape. So either you can do this multiplication of all elements, or you can simply also stack the vectors on top of each other. So you can stack the blue vector on top of the red one, and then you end up with the resulting vector of that addition. The other operation is a simple stretching, or let's say decreasing of the vector length, and this can be achieved by simple multiplication of all vector elements with a single scalar value, and then in this case, for example, the red vector v is multiplied by 2, which is such a scaling operation, ending up with double the length. And in this example, actually, it's a combination of the addition and the scaling operation. So here we have 1 time the blue vector v, and 2 times the red vector w. And again, we do this element-wise operations, or we could simply add up all these vectors and end up with the black one. So these are like the most basic operations for vector space, and they have this nice geometric interpretation. Now I do a short jump to calculus, or let's say basic algebra. So to those who are never seen like a sum sign, I hope most of you did. And the sum sign basically is a shortcut. If you're too lazy to write a row of numbers like 1, 2, 3, 4, 5, you can simply use a sum sign telling you that you have a number or a letter I, which is starting by 1, and then you multiply, you increase this 1 step by step till the last number 4, and you add it up all together. Finally, you get a 10 in this case of the numbers 1, 2, 3, 4. Then I was asking you in the initial questions, well, how about if you sum up all elements from 1 to 40? And the correct answer is 820. So you probably, maybe it would be interesting if you calculated this like using some programming languages or calculator, or whether you knew how there is also a shortcut to calculate this number. So maybe you can just type, I knew the shortcut, or I did it like with a calculator. So what you can do to come up with a shortcut here, you 1 time add up all numbers from 1 to 40, like naively 1, 2, 3, no, 1, 2, and 3 is missing, up to 38, 39, 40. And then you do the same like in a reverse order. So you also add up 40, 39, 38, down to 3, 2, 1. So basically 1 time you add up the numbers forward, and 1 time you add up the numbers downward. So we added up the numbers twice in total, so that's too much. So we need to correct this by taking half the value, and then this formula should actually be the correct result. Now we can look at the single packages here, the brackets in more detail, and we see that each brackets hold exactly the value 41. So 1 plus 40 is 41, 2 plus 39 is 41, and also the ending packages all give the result 41. And then we know that in total we have 40 packages. So instead of calculating all the numbers manually, there's the simple formula. So you can take the total number times the total number plus 1, and then you need to divide by 2. So that's the trick. That's just some short side notice. but this sum sign is usually, it's used a lot in linear algebra. Therefore, I want to make sure that you feel somehow familiar. And another thing, people, if they're long in a field, they're getting lazy with the notation because they know everybody else knows anyway what they're talking about. So they like to write as least as possible. And one thing they abbreviate is the sum sign itself, which is quite tricky. So the rule is in this case, if an index occurs twice in an expression, you need to implicitly assume that there is a sum sign in front of it. So if you have here like two numbers with an index I, which is the same, it must be the same index, then if Einstein notation is active for these context, it's the same as adding a sum sign in front. And what is then always implied that the sum like runs over all possible entries of the dimension of your vector. So the sum sign always starts with the first entry and goes to the very last entry. So you can only use the sum sign if you really want to sum up all possible elements and not just a fraction. So here in 3 dimensions, we have n equal to 3. So this would be the result written out. Okay, now we are safe to tackle more linear algebra, and you see the sum sign is already present here. And we have something like a linear independence between vectors. This is now defined as follows. If we have a set of vectors, so these are now all vectors. So take care now, the vectors are not written in a bold manner, but actually x1 is one vector, x2 is one vector, until the last vector xn. So you have n vectors, and those are called linearly independent if no vector can be represented by the remaining vectors. So this is maybe tricky to understand. So we start now with the inverse, not when they're linearly independent, but the opposite if they're dependent from each other. So a vector can be represented by a linear combination of the remaining vectors is said to be linearly dependent. And this can be written as follows. So here you have the vectors. You cannot use Einstein notation here because we don't sum to the very end, but one element before. So basically, we take all vectors but the last one, and we multiply all vectors by a scalar factor, and we sum it all up, and then we find a resulting vector, and then if this resulting vector is the last vector of our set of vectors, then those vectors are linearly dependent. If it's not possible to define all vectors with this, like combine them with a prefactor and add them together, if this cannot, so if we never can pick scalar values alpha, which as a result give the remaining last vector, then we call it independent. So I give more examples now. The question is whether those 3 vectors linearly independent or not. So the question is whether we can pick 2, combine them, and the combination of 2 of them gives the third one. If yes, they are dependent. So I want to do this now quite slowly. So we take the first and the second vector. So we pick this and that one. We multiply this vector both by one scalar value alpha, and we want to ask whether this third vector can be reached. So now I jump from vector notations to standard equation notation. So I actually have here 2 equations. So the first equation corresponds to the upper row of our vectors holding the first entries, and the second line is holding the second entries of the vectors. So here you find a 3, 5, 5, which is corresponding to the second line here. So basically, this equation here is now explicitly written. So the vectors here are plugged into that equations, and we end up with the following two lines. So what we do now is we solve this first equation for A, and we simply see that A is -2, -3. This is equivalent to the first equation here. So the A2 is just put onto the other side of the equation sign. And then we can plug in this A1 into the second equation. So here you see the A1 plugged into the second equation, and minus A2, -3, exactly these numbers. And now we have an equation which is just dependent on A2. Now we try to solve this equation for A2. So we can multiply this equation by +9. Then we find on the left-hand side that the 3 times 3 is vanishing with the +9, and we just have a minus A2 times 3 plus A2 times 5. So on the left-hand side, we are left with 2 times A2. And on the right-hand side, we calculate 5 plus 9, get 14. So basically, we found that A2 is 7. Then we can plug this A2 back into, for example, this equation. And then we find that A1 must be -10. So we found a solution for this equation, meaning that we indeed can combine vector 1 and 2 and by multiplying these factors and end up with the third one. So we can check this index or element wise. So the first element times A1 gives -10, plus the second element times 7 gives 7. So -10 minus 7, plus 10 minus 7 gives, no, other way around, -10 plus 7 gives -3. So indeed, those are dependent. Can show the same for the second entry. And we are done showing that. So now we go to 3 dimensions. The question is now whether those are linearly dependent. And now I check whether I'm talking too fast or whether you're too shy to ask questions. So I leave this open for now. And yeah, maybe you can just repeat the calculation and tell me whether those vectors are independent or not. So the question is, if you can somehow find a prefactor, add this prefactor to 2 of the vectors, can be different prefactors, of course, and then end up with a third vector. So if this is possible, then simply state in the chat, yes, it's possible. Otherwise, say no, and then I assume you got the result that they are not linearly independent. So maybe you can just post those answers in the chat. That would be nice for me to get feedback. And yeah, you find the definition here in the top corner. So it's time to me to drink something to relax my voice. And maybe the people who mean that they are linearly dependent, they can state the prefactors. So maybe state the prefactors of vector 1 and 2 in order to get the third one. That would be maybe interesting now. So what is the prefactor? Let's call the prefactor. So alpha 1 for x1 and alpha 2 for x2 to get x3. So maybe you can just post the values of alpha. So the scaling factor for the first two vectors. So I need two numbers, alpha 1 and alpha 2. Yeah, perfect. There is the first answer. So and maybe I give you 20 more seconds for people who are new to this. And those who are unsure maybe can just look up the answer in the chat, but I can also show it now. So yeah, exactly. You need 1 times the first vector minus 2 times, minus 2 times the first plus 1 time the second vector, and you get the third one. Cool. So next, then we have something like a span, and basically a span is the set of, if you have a set of vectors from 1 to n, the span are all vectors which can be obtained by linear combination of the set. So yeah, you can basically combine vectors together to get new vectors. Those, of course, will be linearly dependent, but all vectors which can be reached by a set of vectors by linear combination, as you did in the exercise, are called so-called span. So that's just a definition. And one useful property now is if you have indeed like n linearly independent vectors, then you know that this vector can reach the whole space n. So in case you have n vectors and they're linearly dependent, then you won't be able to reach any point in your space. So now this is a simple question, since you answered a more complex case already. Are those vectors here linearly dependent? Yeah, actually independent is a question, and actually the answer again is yes. So it's impossible to multiply the first vector by a scalar and get the second one, because the first vector has a 0. So this 0 here will never be able to reach the position 1 of the second vector, or to reach the position 3 of the third vector. So yeah, this is a quite easy vector set, but actually this vector set is really used and common because it forms a natural or standard basis of our three-dimensional space. And this is, let's say, the most natural or simple way to reach all points in 3 dimensions. So if you have these 3 vectors, then you can reach all points in 3 dimensions because they're linearly independent. And those vectors are like especially simple because they only have 0s and 1s, which of course are, let's say, more simple numbers. They also have more properties. I go into detail of those properties later. They are normalized, meaning the length of all these vectors is 1, which is also nice simplification. And they're also orthogonal. So meaning there's like a 90-degree angle between 2 of these vectors, or mathematically speaking, if you multiply all elements point-wise or element-wise of 2 vectors, you always end up with a 0. So if 2 vectors ending up with a 0, then they are orthogonal. So here, this is of course only the case if you take different vectors. So if you multiply the first vector with itself, then you get 1 times 1 and 1 as a result. But if you pick different basis vectors, then the multiplication is always 0. And this is a definition of orthogonal vectors, meaning 90 degrees between them. And yeah, most often, like geometrically, you represent those vectors in a right-handed coordinate system, which is shown here. Actually, this is like a bill of Swiss money, like I think 200 francs or 200 Franken. And here they have like this rule how those basic set of or natural set of vectors most often is represented. Namely, the x vector is the sum, the pointer is the y vector, and the z vector is the middle finger. So, and this is one typical way how these vectors are then depicted graphically. But, and this is not the only way. For example, you could also have a different orientation using the left hand. So I just wanted to point out that these vectors, they stand on its own. You're sure you can reach all points, but the graphically representation can be different. So you can either organize them on the right or on the left hand if you draw a picture. So this is just a definition of context. Okay. Then I want to talk a little bit about bases. So we already got one options, like to span a base in 3 dimensions. Of course, you can also define a base in n dimensions, and this would then imply that you need n linearly independent vectors. And yeah, there are many bases to choose from. So the simple base we saw before is only one option. Now we stick for now with a very simple base, just in 2 dimensions. And if we now multiply a base consisting of all the basis vectors, so we have a vector I1, E1, E2 in 2 dimensions, and so on till n dimensions, and we multiply all these vectors by all these basis vectors E by another vector X, and the X is basically just holding scalar values as its entries, such that if we do this multiplication, I will show you how to multiply this properly later. But what we want to do now, we want to multiply the first element of this vector with the first basis vector, second entry with the second basis vector, and so on. And then this vector X basically provides a list of coefficients for all basis vectors in order to reach a certain value X in our space. And in 2 dimensions here, we, for example, shrink a little bit the first basis vector, let's say by half. So alpha x1 is half, and the second vector, the second basis vector E2 is stretched a little bit, let's say by x2 is 1.5, then the second basis vector is stretched, and then we add up those 2 vectors by our properties of our vector space, and then we get the final vector X. So this is, let's say, simple representation, and a vector basically can be used as a carriage for coefficients applied to basis vectors. So yeah, this sounds complex. Basically, you could also define directly that the first component of X lies in the X1 axis, and the second, per definition, lies in the X2 axis. And this is what you most naturally do. So implicitly, you always basically assume that you have this natural basis when you draw vectors in this coordinate system. So my first example with this rotating vector actually pre-assumed that we have this interpretation of basis vectors, which doesn't necessarily need to be the case. So this representation of X is only true for this set of basis vectors. And just to give you an example, now I say, okay, I don't care about the simple basis vector. I change the second basis vector for, let's say, this black one, this F2. And then, of course, if they're linearly dependent, I'm sure I can still reach the same position in space X, but I can only do so by using another scalar coefficient in front of my new basis vector. And of course, if we assume that those vectors, that the vector here provides coefficients in this basis, meaning the basis is a combination of the E1, E3, E4 till En plus, instead of the E2 and F2, then if we interpret the coefficients of our vector in this basis, we have not the proper coefficient for the second basis vector, meaning we end up somewhere else. So yeah, so keep in mind that if you want to draw a vector in like 2 dimensions using this simple coordinate system X and Y, then you always basically assume that you have this natural basis, but a vector can also be something else, or the coefficients of vector can also correspond to another basis, or actually, as in my examples, the coefficients, they do not necessarily need to have a geometric interpretation at all. The coefficients of a matrix, they can be like densities or velocities of my fluid flow, if we are talking about like fluid mechanics. Or the coefficients, of course, can be like pixel grayscale numbers if we have a picture. So there's a question: the X1 coefficient should change to if you replace E. Well, of course, if I change also the first basis vector, and then I also need to change the coefficient for the first basis vector. But in this example here, I was only changing the second basis vector. So the first basis vector stays the same. The second basis vector is different. Such I only need to adopt the second coefficient to reach the original position in space. So I hope this answers the question. So the X1 coefficient should not be changed. The problem is I don't replace E1. I keep E1. So the basis vector E1 is replaced, but I only replace E2. I think that's maybe the confusion. So let me know if that's clear. Perfect. So then we define something called a rank. The rank basically can be calculated different ways. One way is to calculate the so-called column rank. And the column rank basically counts the number of linearly independent columns of a matrix. So if you imagine yourself a matrix, maybe I can also like draw it here. Let me see. Pointer options, pen color red. So if we have a matrix here, then basically we can split up the matrix entries in individual columns. And if these columns here, the number of columns is all linearly independent, then we call the number of columns our rank. And in case one vector is dependent on the others, we have to reduce the rank by 1. So n is the total number of linearly independent vectors. And the same applies for rows. So you can also like do this in the row picture. So you can look how many rows there are and whether those rows are linearly independent or not. And then you count the numbers of linearly independent rows, and this gives you the row rank. And one can show that actually the row rank is equal to the column rank, and hence we can simply speak of a global or just a simple rank of a matrix, which either can be calculated by looking at the columns or by looking at the rows. Okay, I switch back to my pointer. So we have here now two examples. So the column rank is the number of linearly independent columns. In this example here, I have a matrix. And if we look at the second column and third column, we see already that at least they are close to each other. So if I multiply the second column by 2, I nearly get to the third column. I'm just missing like 2 here and 2 here. So I add 2 times the first column plus 2 times the first column plus 1 time the second column gives me the third column. So meaning the third column is linearly independent from the other 2. So we have 2 linearly independent columns here, such the rank of this matrix is 2, while the dimension of the matrix is 3. So the dimension is simply here the number of entries. In the case of a square matrix, it's column numbers and the row numbers is both 3. And here we have another example where we actually have only independent vectors. So here again, if there are many zeros, this is a first indication that it's hard to find a linear combination using a 0, because you can never multiply the 0 with something which ends up being a 6. And so the second vector can never reach the value of this third vector. The same applies for the first vector. He has zeros in 2 columns, and you're never able to multiply the first vector or the first column vector, I have to say, by something to reach any of the other 2. So they're all linearly dependent. So we call the rank 3. And this is actually the maximal rank you can get. There are only 3 vectors inside. And this is what we call full rank. So I just could give you some more properties of the rank. So if we have a matrix with a dimension m times n, then the rank of this matrix is always smaller than the smaller dimension. And at best, the rank can be as big as the smaller dimension of the matrix. So if n is smaller, let's say, then the rank can be at least as big as n. And if this is true, so if the rank is as big as the smaller dimension of our matrix, then we call the whole matrix to be full rank. Also, we know already that or I told you actually, you need to, it's a little bit more tricky to show it. There's time missing today, but I told you that the column rank is equal to the row rank. And so since the transpose is basically switching between columns and rows, this basically is stating that the column rank is equal to the row rank. And then we have the property, again, now we need matrix multiplication, which comes later in the slides. I just pointed out here that the rank of the result of a matrix multiplication is always smaller than the smaller rank of either A or B. And more simple for matrix addition, we can imagine why the same is true. So the rank of the result of the matrix addition is smaller than the sum of both matrices individually. So this you can understand somehow that at best the vectors in A and B are linearly independent between each other, meaning if you add both, you at best can keep the rank of these two. But if you happen to have a linearly dependent vector, so one vector in B is linearly dependent to a other row vector in A, then this combination won't increase the rank further. So at best, you can keep the rank or have a smaller rank after multiplication. After addition, sorry, I'm talking here in the last row about the addition. So now I come to another property of a matrix, which is a singular value, so-called determinant. So if we have a determinant is only, you can only calculate it for square matrices, so the dimension is n times n. And the determinant itself is a single scalar value. So you start up with a matrix with dimensions n times n, and the result of this operation is a single scalar value. And yeah, we are here in real space, always nothing new. To note that we want to do this operation of the determinant, usually you just do like a vertical bar or upright slash around a matrix, and this indicates you want to calculate the determinant. Or what you usually do, you write det A. Actually, yeah, this can be misleading, especially in the beginning, since most often those upright slashes or vertical bars or pipes, if you are a programmer, they are used if you calculate the absolute value. So there is like a ambiguity. So for you as a reminder, if two such vertical bars are applied to a vector or a scalar value, then this should be interpreted as an absolute value. While if you apply two vertical bars to a matrix, then most people always mean that you calculate the determinant of that matrix. So depending on the object you apply your vertical bars, it does something different. So that's like general rule to know this. Now I simply tell you the cook receipt for 2 and 3 dimensions, how to calculate the determinant. Yeah, in 3 dimensions, beyond 3 dimensions, you never have to do it by hand. And yeah, in general, in linear algebra, also like simple thing like a vector multiplication is best for big systems to do with a computer and some programming languages, because there are great linear algebra libraries made by like professional informatic people who know how to get the most performance. And there's like a lot of interaction between the mathematics we focus on here and the actually architecture of your machine. And yeah, it's always tough to learn the architecture of your machine. Usually you are happy if you understood the math, and then this takes a lot of time to understand. So if you use a linear algebra library, then you simply tell the library, yeah, now I want to do the multiplication, or I want to calculate the determinant, and then the library is doing the job. And then you save a lot of time, and you have the most efficient implementation. But of course, if you want to develop methods and develop your own models, you need to have an understanding, and therefore, like all the math bases are important too, like to understand the principles, at least like have some feeling how things can interpret it in, let's say, in a coordinate system. And this is helpful if you want to develop a model, and also if you want to have a quick glance if something makes sense. Like otherwise, you just stare at numbers and you never figure out, yeah, whether this can be true or not. So these concepts help a lot to get a visual intuition of the things, and therefore we spend time here. So now back to the cookbook. So if you do it by hand, basically in 2 dimensions, I define here that the green arrow comes with a plus and the red arrow comes with a minus. And to calculate the determinant, you multiply the diagonal entries, like A11 times A22, and then you subtract the elements like opposing the diagonal, minus A12 times A21. And in 3 dimensions, it's even more work. So here we start separating the problems into 3 two-dimensional determinants. And what we first have here, like, is a green A11. So maybe I go back 1 slide. So there's the pattern of alternating signs, which is like associated with the first row here. The first entry comes with a plus. So we pick this, and then we calculate the two-dimensional determinant as before, which is just written here. So positive, the diagonal elements, plus minus the elements beside the diagonal. Then we can calculate the next bit of our 3D matrix. So this time we have like a negative sign of our entry A12. We place it here, and again we cross out all entries which are in the same column or same row as our A1, 2. So this is in the same column and same row. We cross that out, and we are left again with a 2x2 matrix, and this 2x2 matrix is again treated like a normal matrix, and then we simply can like calculate the diagonal minus the elements next to the diagonal. Here I just write that we calculate the 2D matrix, and last but not least we pick the last element with positive sign. We sketch out the entries in the same row and the same column of this green A13, and we are left again with a 2x2 matrix, which we calculate according to the roots of a 2x2 determinant. So great. Now I already appeared at the first video, so I think maybe that's a good point to do a first 50 minutes break. But yeah, there's a problem now with the copyright of that video. So I'm unsure whether the guys joining via a YouTube stream, they can watch the whole video. But basically what you can do, you can either Google for this name here, Essence of Linear Algebra, chapter 6, the determinant, and or you just type in the link and then you can watch it in case there's a problem with the YouTube stream. For sure on Zoom we can watch it all together. I think this should work flawlessly. And yeah, later when I upload the slides, I told you I cannot include this video anymore, but I will remove this video. So as of since first I want to just point out that in the video the guy is talking about so-called linear transformations, and I just want to remind you that the linear transformation is the operation matrix is doing. So we're focusing so far on just the object itself. So we're focusing on a vector and a matrix on its own. But actually now the next part after the break will be how to combine those objects together. So how to combine two matrices, how to do a matrix multiplication and how to add a matrix to a vector. And this video already, the focus is on the process of a matrix as an acting entity. So a matrix can be considered as an object just holding elements on its own and doing nothing, but actually the matrix can be also considered as doing something on a vector. And this doing something is called in linear algebra linear transformation. So a matrix in linear algebra cannot do all types of operations, but only the linear ones. And yeah, one example we saw was the first example of the rotating vector. So a matrix was rotating this vector. And another example is like matrices who stretch something. So stretching and rotating is a typical thing a matrix does. And this stretching and rotating then can be visualized, for example, in the standard basis we just saw. So maybe that's enough for like introduction for this presentation of or interpretation, visual interpretation of the determinant. And then I would say, so what's the time now? So the video is like 5 minutes, and we said we have 15 minutes break. So, and let's say the video ends at 11:40. So let's maybe resume. Yeah, 11:55. Well, that's close to 12. So I hope everybody is back. So maybe I start answering the questions, and then the people who come in a little bit later don't miss anything. So I share my screen again. Which one? That one. Okay, cool. So there was a question regarding my change of base and regarding the prefactors of the basis vector. I'm keeping the first basis vector the same, but actually, as correctly mentioned, also the index, the coefficient in front of the first basis vector needs to change if I switch the basis. And this actually happens already if I replace only one basis vector, in this case, the second one. And to make this clear, why also the other coefficients need to be adapted, I extended my figure, let's say, namely the green arrow here at the x-axis corresponds actually to the product of c1 times the first basis vector, which must be now longer. The green arrow now here is longer than the original product x times the first basis vector, which is shorter. And this is otherwise we won't end up at the same position x as before. So if we want to end up at this point, which is the whole point, that we have a point in 3 dimensions, which we want to express in terms of our basis vectors, then we want to end up at the same position. So maybe I draw this to make it even clearer. So where's my pen? So I use the black pen. So let's assume here a basis system. So this is x, and this is the coordinates. And then this point here is the point we want to end up. So we have here now a basis vector. I redefine that basis vector. Instead of using a natural base on the y-axis, I said, okay, I want to have another basis vector, f2. If we stick to the original basis vector on the x-axis, and we add up those two vectors. And basically, yeah, we have this parallelogram, and the resulting vector would be here. And this apparently is not the dot we wish for. So maybe I can change color. So pointer option, pen color. Let's say, I actually want to end up at this point. So we need also to correct the prefactor on the first basis vector, which is this one. So we stretch the first basis vector a little bit further, and then actually the parallelogram, which is like the geometric interpretation of a sum of two vectors, ends up at our desired point. So only if we alter the second coefficient 2, we actually make this change of base possible and stick to the same point. Okay, that's for the comments. So I want to now jump back to my original slide. Card. So where's my the video? And now I put my screen on again. So now we are back. So welcome to, well, no, I don't need the Zoom chat. Okay, got it. Okay, there are no more questions. So I'm glad that you all understood the video, hopefully. Yeah, maybe it becomes even more clear when we actually start doing matrix multiplications with vectors. But yeah, I think that the first thing now so far should be clear. So welcome back to the second half of the linear algebra. I resume now to visualize the determinant myself. So for those people who haven't watched the video, the main point of the video was to show that if you have a matrix and the matrix consists or can be interpreted to be consisting of two vectors, these types of vectors are 1 and 3, the first column, and the second column gives the vector 3, 2. Actually, those vectors should have different numbers. So imagine there is a 2. Otherwise, it would be the same. No, I don't correct this now. This is not important. I think you can imagine that here's a 2. So actually, in the drawing, it's correct. There's vector A1 and a vector A2. And the area of this parallelogram, or if we are talking about n-dimensional matrices, it's a parallelepipede. The area is actually the absolute value of the determinant. So the determinant gives a number, and this number is the area of this parallelogram, which is created by the both column vectors of our matrices. And yeah, the sign of the determinant can change. And you can do this, for example, if you flip those two vectors, then you flip somehow the orientation of the area, and then the sign is negative. But if you take the absolute value, since an area needs to be always positive, you get basically this space. Yeah, so yeah, I also wanted to mention that one important case is when those two arrows here are parallel. This means they are linearly dependent. So if the two column vectors are linearly dependent, this implies that the vectors are pointing in the same direction or in the opposite direction, but if they're linearly dependent, they are parallel, then the area between two parallel lines is 0. So this geometric interpretation is already like quite powerful to understand linearly dependence between vectors. So if the determinant is not 0, this means that they are linearly independent, while if they are dependent, then we have a resulting 0 volume, and hence we call them linearly dependent. So if you calculate the determinant, you now have a, let's say, easier recipe to tell whether vectors are linearly dependent or not. So now it's your turn, I think. So I have one question for you, like to wake up after lunch break. Well, it was a short one, but nevertheless. So how big is the gray area between these two vectors? So this question is a little bit tricky because I do not ask for the surface of the whole parallelepiped or the whole parallelogram, but actually the space just between the two vectors is half of it. So if you now calculate the area of this gray thing here, then yeah, you need to take care of that. So please all plug in your values in the chat. That would be nice. So yeah, you can of course pick up the recipe how to calculate the determinant a few slides before. So maybe for people, so the vectors are, maybe I write it down, one is one vector, vector 1, and then we have another vector, which is so this is just the input vectors for you as a reminder, and then I show you the recipe to calculate this determinant, so that everybody has a chance to do it in case he doesn't remind that. So I think that's looking pretty well. I drink some more water, that's always good. Oh, yeah. I think I continue. So nearly everybody got the proper answer, which comes now. So we need half the value of the parallel of the whole determinant, because the whole determinant I can also draw it. Maybe would be what options I need again, my pen. So I need to do this in parallel. This is somehow parallel to that one, and this should be parallel to this one. It's tough. So this line should be this line, and this line here should be that line. Yeah. Well, somehow this is would be the full area of the determinant, and we only need half of it. So we take half the value, and then we write down that we calculate the determinant, and we, to be sure, maybe the determinant is negative, I take the absolute value of the determinant. So we end up 1 times 2 is 2, minus 1 times 1 is 1. So 2 minus 1 is 1, and we end up with 1/2. So yeah, maybe visually you can somehow see that this makes sense. So yeah, now you have a way to do some geometric operations with the determinant, one application already, but there are plenty of more. Mainly it's important like to determine linear independence or linear dependence. So if the determinant is not 0, we have a linear independent set, and linearly independent sets are important, for example, to define a proper basis of a coordinate system, but there are more applications. So, if we have like a identity matrix, this was the matrix with all diagonal entries 1 and the rest is 0, then you can easily, then the determinant is 1 in all dimensions. For 2 and 3 dimensions, you can calculate it yourself now. Then you can multiply a single row by a scalar value. So you pick one row and you multiply all entries in that row of the matrix by one value, let's say t. And then the determinant will be simply t times the original determinant. Also, we can exchange 2 rows of a matrix, or we can also exchange 2 columns, and then the mu determinant will basically just flip sign. And also we can say, this is what I was pointing out with the graphical interpretation all the time, that if we have a matrix and the determinant is not 0, we know that this implies that they are linearly independent. So if all vectors of a matrix are linearly independent, we call this full rank, because the rank was the number of independent row vectors, for example. So there are even more properties. For example, the determinant is the same whether you switch columns and rows. So the transpose operation is basically just switching column and rows. Then again, it's like a teaser for vector multiplication. So if we do vector multiplication of 2 matrices, the resulting determinant is the same as the determinant of the individual matrices A and B. Actually, I want to switch back to the laser pointer. Otherwise, you don't see my pen, I guess. And now we are at the third property, the more property list. If a determinant is 0, then we know it doesn't have the full rank. Then we know they are linearly dependent. And if the vectors or the columns of the matrix, I should say, are linearly dependent, we call that matrix singular. So more details follow on that. Last property is that if we have a matrix and the determinant is not 0 or not singular, then we know that we can somehow have inverse of a matrix. This is also a teaser. So inverse of a matrix comes later. The inverse of a matrix is denoted by -1. So it's another operation, let's say, as transpose, different. And the determinant of the inverse matrix is the same as the determinant. And then you divide 1 over the value of the determinant. So just the inverse of that scalar value. So since it's really easy to determine the determinant, and it's easier just to do this division, this way is very faster to calculate the determinant, then first do the inverse transformation, because this inverse operation is more expensive. But yeah, this is just a real property you can recall someday. So next chapter now is most important, how to combine matrices. And actually with this also the combination of matrices with vectors are included. And we start here with a matrix multiplication. So we have two matrices here, one matrix A with the dimension m times n, and a second matrix B with the dimensions n times p. And if we multiply those two together, we can either denote it by a dot, but most often people tend to do not do anything as notation, but they just write A, B behind each other. And then the result of this matrix operation is C. So this operation now is slightly more complex because it's not a pointwise operation in a trivial sense. So pointwise would mean that you take the upper left element of A times the upper left element of B, and this gives you the upper left element of C. So this is like a trivial thing to you would do if you multiply, if you add those matrices. So if you add matrices, if you subtract matrices, then you do this always element-wise, and the element of A corresponding to the same element of B is added and gives the element of C. With matrix multiplication, you need to combine more elements together, and this is somehow denoted in this picture here. So if, for example, you want to calculate this element of the resulting matrix C, which is called C12, which is corresponding here to this red line, then you need to multiply the whole column corresponding to this entry of the resulting matrix of matrix B times the whole row of the first row of matrix A. So matrix A, you always look at rows. Matrix B, you always look at columns. And then you combine all elements element-wise, and you add up the whole thing as a sum. So this can be written now in this manner, that you sum over all element k's. So the k of matrix A is running here in the horizontal direction. The k is the second index. And the k of matrix B is running in the vertical direction. It's the first index. And if you sum up all these elements, all these products, you get the resulting matrix C entry. And this you have to do for all entries of the resulting matrix. So you do much more operations than like if you just add matrices. You always add the whole row of A times the whole column of B. And here again, I could write this even simpler using the Einstein notation. So since I'm looping over all elements, I can drop the sum sign and could also just simply write it as A with the index ik times B with the index kj. And then this basically implies that I'm looping over all k's and sum up those. And yeah, here it's basically written down what is done for those two elements, but of course you need to do it for every position in the final matrix. Here I want to just give a hint, like in different programming languages, there are different notations. And actually, there is always, if you want to do a matrix, or if you want to do any operations between two objects, you always need some kind of sign. I think there's no language where there is no sign at all, but I'm not 100% sure here. Most languages have some kind of sign, let's say, and it's like sometimes pointwise, and sometimes they mean the real matrix multiplication. So depending on the language, sometimes it's really safe. They have like a whole function, which, for example, could be matmul, So in NumPy, for example, I think it's matmul. And then this is clear that this is a matrix multiplication. But there are other languages, for example, like Mathematica or MATLAB, but there are many more. And they have like, they use a dot or like a star to indicate a matrix multiplication. But they also use a dot, for example, or a star to indicate a pointwise multiplication. Of course, each language only uses one sign for one operation. So within the language, it's always clear. But if you jump between programming languages, then make sure that you understand what this is actually is meaning. Okay. So now we start with an example. I now do it like bit by bit. So we have here one matrix where we take the upper row and multiply it with another matrix where we first look at the first column. So we have here 1 times 1, 0 times 3, and 1 times 5. The result is 1 times 5, which gives me the first entry. And then we can continue. Now we're looking for the next upper right element. So here we take 1 times the first element of the second row, the second matrix, 1 times 2, 0 times 4, 1 times 0. So here basically just the 2 remains. And you can imagine how this goes on. So now we are looking at the lower row of the first matrix, and we're doing the pointwise multiplication with all elements of the first column of the second matrix. 0 times 1, 0, minus 1 times 3 is minus 3, 1 times 5 is 5. And so we got here minus 2, no, plus 2, sorry. And the last element now is given by the lower row of the first matrix times the second column of the second matrix. So we have 0 times 2, 0, minus 1 times 4 is minus 4, and 1 times 0, another 0. So it's just the minus 4 remains. So this is actually, yeah, straightforward. And for small matrices, it makes sense to do it on a sheet of paper just to get used to that. And yeah, soon then you, for sure, you use a computer. And but in the beginning, it makes sense, especially regarding the dimensions. You can make many mistakes if you're programming, that some operations complain, yeah, I cannot be multiplied by another thing because there's a dimension mismatch, and this dimension mismatch is originating from the problem that you need to understand that there is a change in dimension, and only certain dimensions can be multiplied. Maybe I forgot that to tell that in all clearness. So in order to multiply two matrices, the number of elements n in the first matrix needs to be the same as the number of elements n in the second matrix. So these two n's, they need to have the same value. Otherwise, you cannot apply this row times column rule, and then the matrix multiplication is not defined. So you need to make sure that those dimensions match, and they also need to match like in a special manner. So if you flip those A and B, it can happen. In this case, example, it won't happen, but it can happen that you cannot multiply them anymore. So even flipping then makes it impossible to do the multiplication. And yeah, so that's for this. So now I want to define two vectors and multiply those. So here again, the same rules apply, similar to matrix multiplication. In case of vectors, you have never such a dimension mismatch. The operation is always working. But yeah, depending on how you do the ordering of the vectors. So here, this is again another prove that the ordering of matrix multiplication really matters, you end up with a different result. So if you first pick vector 1 and then vector 2 is the row, vector is the column, vector 1 is the row, then you write it down similar to the matrix multiplication. So you have the row on the left times the column on the right. So 1 times 1 gives 1, 0 times 2 gives 0, minus 1 times 3 gives 3, and you end up with a minus 2 as a simple scalar value. So this is also called the inner product. This is just the definition, like if you set up two vectors in such a way that the result is a single value of the matrix multiplication, then this is the so-called inner product. And then we also can reverse the order of the vectors. So here the row vector v2 comes first, and the column vector comes first, v2, and the row vector comes second. And again, we write the matrix down, and now we apply the same rule. Column here times a row of the first matrix times column of the second. Vector kind of is a one-dimensional matrix, so that's why I call it vector matrix in this context, because we're doing matrix multiplication rules. And we end up 1 times 1 gives the first entry, 1 times 0 gives the second entry, 1 times minus 1 gives the third entry. So the ordering really matters, and the outer product of two vectors actually creates like a whole matrix. Of course, you could also like interpret this, for example, that the column vector here is kind of basis vector, and you do three, you stretch this vector 1 time by 1, and then the vector stays the same. You stretch this vector by 0, then you get the 0 vector, or you multiply this vector by minus 1, and then you get the minus 1 vector here. But yeah, this is now basically a whole matrix. So all the same rules apply again of matrix multiplication, also if you combine vectors. The matrix multiplication is associative. So it doesn't matter if you do first matrix multiplication of A and B, and second matrix multiplication of B and C. So you can have like arbitrary brackets. Also, we could verify this. So yeah, this is a common thing if you attend more linear algebra classes and you need to do homework. This is like a typical thing would be part of the homework, that you like need to prove that this is actually true, that you can change the order of brackets. And what you usually do then, you look at one single element of the matrix. So you look at the resulting elements of this whole matrix multiplication, A times B times C, and you look at the element ij, and then you plug in basically the definition for matrix multiplication one by one. So first, now we start with the matrix multiplication of C times the result of AB. So this is then the definition. AB is basically the first matrix, and C is the second matrix. And here we sum over all element case. And then we look into the AB matrix multiplication, and then we plug in again the definition again for AB multiplication. And yeah, I don't want to now waste too much time with the details of the proof. Here you find it in full length. But yeah, finally you end up showing that you can switch the ordering of the sums. So if you have a multiplication of scalars, you know how to deal with them. So here we are just talking about scalar values. So by plugging in all definitions of the sum signs for matrix multiplications, we end up And by picking just one value, we show this proof for one value only. We end up only with scalar values, and you know how to multiply scalar values. And you know that if you have like many multiplications and summands, you can reverse the order. And this way, you can now do here some flipping of the brackets and finally plug in the definitions and find that this property actually is valid. So, and there are more properties. They are distributive. So you can either first do addition and then the multiplication, or you do the matrix multiplication before you do the addition. And also this you could show like picking a single element. And also we saw already, like for example, of our vectors, that the ordering really matters. So it's not commutative. So here comes another example. I think you saw that before. The identity matrix has ones in the diagonal and zeros otherwise. The identity matrix is like the neutral element of matrix multiplication. So meaning if you multiply a matrix by an identity matrix, then you do not change at all the values of the matrix, but the matrix stays the same. And of course, this is true if you do this matrix multiplication with the identity matrix also from the other side. So yeah, it basically changing nothing. And one thing to note here, that depending whether you multiply the identity matrix from the left or from the right to A needs to have a different dimension, because the matrix multiplication requires, per definition, that there is like this matching index. So this row here implies that this I has a different dimension from that I. It's made such a way that this multiplication is possible. This is just a side note. So the identity matrix definition is quite, context dependent, let's say, from the matrix which you apply the identity matrix to. So this is nothing new now. This basically just now, giving fancy names to things you saw before. So we calculated a row vector with a column vector, and this is what and you end up with a single scalar value, which is the sum of all these products. So this is just a repetition, but to give you the names people talking about, we call this a scalar product of two vectors, or inner product. And this product of two vectors is used a lot, and there are different notation variants again people use. So I would say the most intuitive one is really the definition that you have like two row vectors, and you need to flip the first row vector to make it you have two column vectors, x and y, and you need to flip the first column vector to make it a row vector. So the first vector needs to become a row vector in order to do the inner product. So if the t would be standing at second vector, then you would calculate the outer product. So the inner product is always row times column. And of course, again, you could use the more clear vector notation with bold font. This is especially done like in digital documents where you can actually see a bold font, while like if people write on the blackboard, the bold font is shitty to see, and then people like the error notation again. And also sometimes people don't indicate that you actually need to rotate or do the transverse operation to get the row times column, well, they simply write 2 times the column vector, and then this dot here is another way to tell you do the inner product. So if there's a dot, this usually always applies, means that you want to end up with one scalar value, which is this here. And yeah, there's also the way to use like this brackets to define this kind of operation. And the inner product is symmetric, so you could in case of vectors also flip the order, but of course still you need to first have a row and second a column. Otherwise you do not shrink down to a single value. This is of course not true for matrices, just for vectors. And then if you have 2 orthogonal vectors, then the dot product is 0. Basically, I was telling you this before, but now we properly introduced the way vectors and matrices are multiplied together. The outer product is also what we saw before. So this time we have first the column vector and second the row vector, and then we end up like with a full dimensional matrix, and this is called the outer product. Okay, great. Next, I want to now do the vector matrix multiplication. So this time we apply a matrix on a vector. Actually, we also did it before, but now we know the rules properly. And one way to do this vector multiplication is to stick to the matrix shape and simply add the first element of the row vector to the first element of all rows in the matrices. So the x1 is here appearing multiple times. The x1 is multiplied times all the first row elements, and the second element in the column vector here is multiplied to the second row element of all matrix rows and ends up here. So this time you see the value many times. A more compact way to write this down is to simply split out the matrix into columns, and then the first entry of the vector is multiplied times the first vector. The second entry of this vector is multiplied times the second vector. So this is actually also what was, for example, visible in the video, and what we did many times before, like with the multiplication of our rotation matrix. So we had the vector 1, 1, and basically we could now apply the same rules as here, and now we understand really how a matrix operates on a vector. And another thing in the video, for example, I maybe write this down here. Let me take a pen. So if we have a standard base vector of the 2-dimensional space 1, 0, then we can now apply some matrix multiplication. Like in the video, he was, I think, picking some more or less random matrices, and yeah, it's the same principle as before, but now yeah, we can repeat it again, and the result would be 1 times 1 is 1, 0 times 2 is 0, so here's 1, and this just gives a 0. And this guy here was in the video, and also in my slides, the first natural basis vector. So this like normalized and therefore especially suited as a basis vector, has a length of 1. And now in the video of the determinant presentation, he was looking how the linear transformation of this matrix acts on this vector. And yeah, in this case, it doesn't change the vector at all. So maybe that's a bad example. So let's add here an 8. So then we need to repeat the lower row. Then we get here an 8. And then the linear transformation on this basis vector will actually change then the basis to 1, 8. So the result would be way up somewhere here at position 8 in y direction and 1 in this direction. So this can be drawn in the y direction, and this corresponds to the x direction. This is the x-axis. This is y-axis. Okay, so this visualization in the video basically was just rotating the basis vector by some matrix operation, and then he visualized the result where this vector ended up. Okay, so basically now, yeah, we also did this before many times implicitly. Matrix times a vector, simply a linear combination of the columns of the vector. So the vector holds the coefficients A1 and A2, and those coefficients give the so-called linear combinations of the column vectors of the matrices. Okay. Next, I want to introduce the column space. So if we do a linear combinations of the column of vectors, we can fill a certain space. And yeah, again, here I define a matrix with the dimension 3 times 2. And we assume that this matrix has 2 independent columns, vectors A1 and A2. And then, yeah, it's basically just a repetition. The matrix now, or the column space is basically just the space of the matrix, which can be accessed by doing the multiplication of the matrix columns with a vector. And yeah, as visualization, for example, in 2 dimensions here, we have 2 vectors, and this is the space you can reach. But of course, actually, the space is even larger, so I do not like this color area here too much. It's also could be going to the negative A2 direction and to the negative A1 direction. But one thing to point out here, that the matrix A can have an even larger dimension in one component. And then if the matrix has like not a is not fully 3 times 3, but has only 2 linearly independent vectors, then like in this example here, then you only can reach a surface or a plane inside your 3 dimensions. So even though the result of this matrix multiplication ends up in a higher dimension, you won't reach every point in this higher dimension in case, for example, your matrix has not like full rank. And so this is maybe important to keep in mind that with a matrix multiplication, you can even extend the dimension. Like, for example, I can also draw it. Let's say we have here a vector, and so the matrix needs to have the same number of elements in the row as the vector has in the column. But here in this second dimension, the matrix can be really big. So, and so you see that the resulting vector of this matrix multiplication can be bigger as the initial vector. But since here we do not have enough, let's say, basis vectors to span the whole space M. So if this is the dimension M, and this is the dimension N, and N can be larger, but there are only N basis vectors, meaning to reach every point in bigger M-dimensional space. So here in 3 dimensions, we would also need at least 3 basis vectors, which are linearly independent. Since here we got a lower number, namely only 2, we can only reach the surface. Okay. So can I remove this? Eraser. So cool. Back to the laser pointer. So the column space is also called range. And as I mentioned before, the range can be like a 2-dimensional thing within a 3-dimensional place. So it doesn't necessarily fill up the whole dimensions. So I want to visualize like all possibilities a matrix multiplication can do. So here, matrix multiplication times the vector. So you have here a matrix A and then an input vector X, which is living in the dimension N. And the result of that matrix multiplication is the vector Y, which is living in another dimension, namely M. And and this other dimension can be bigger. So this like circle here can be bigger than the initial rounded square here. But most likely now, if you do a operation and your matrix has like not enough basis vector to reach the full space, which is always the case if N is smaller than N, then the range is like a subset of the whole space you could possibly reach. So the range this matrix is accessing is a smaller bit here, which is indicated by this red square, which is inside the whole possible space. And then there are some special results, namely if this Y is the null vector, so all input vectors X multiplied by our matrices, which are ending up on a 0. Basically, it's a 0 vector with many zeros here. It's just indicated here by a bold 0. And all these input vector we call the null space. So the null space are those input vectors who end up on a 0. So this is like some general picture where the result of a general matrix multiplication times the vector ends up. Great. So see no questions. Then I go on to some more properties of matrices. So one important is the so-called trace. the trace is basically only defined for a square matrix and is the sum of all diagonal elements. So again, here I could use also, no, I couldn't use the Einstein sum notation here because I need two independent variables, each with the same index. Here actually it makes sense to write down the sum sign, indicating you want to sum up all elements on the diagonal, and this is the trace. The trace of a transpose matrix, so if you switch column and rows, it's exactly the same. So yeah, you can see this easily if you switching column and rows, the diagonal stays always the same. And since the trace only picks up elements from the diagonal, it's obvious. Also, you have like, again, multiplication properties of the trace. So either you can first add two matrices and then calculate the trace, or you can do the trace of the individual matrices first. Also, you can multiply a whole matrix times t. Of course, multiplication by a scalar t is element-wise. So all diagonal entries end up with a t, meaning the whole trace result is increased by a factor of t. Also, you can look at the trace of a matrix product, and actually what you will find out, of course, you could again prove this as some kind of homework, looking at individual elements, plugging in the definition, the matrix multiplication, and you can see that the trace of AB is the same as if you inverse the order of matrix multiplication. So normally, inversing and like inverting the order or changing the order of matrices is like making a big difference. So keep in mind that usually changing the order makes a difference, but just in this special case, not of the trace. And also you can have like even three matrices multiplied together, and then you find that the trace of the three matrices ABC is the same as if you do some cyclic permutations, meaning you here take the A from the beginning and put it to the very back, which gives you the second entry here. Then you can again take the B from the beginning, put it to the very back. This is now appearing here at the very back. C comes to the front as second index. And yeah, if you always take the first matrix, put it to the back, then this is what we call a cyclic permutation. Okay, great. Last property, so-called trace trick. So if we have a vector times a matrix, then you see that if you multiply a vector for some matrix, I maybe can also highlight this simply by some drawing. Pointer options and color black. So we have a matrix and we multiply a vector. Then we do this like row times columns. We end up with a vector. So now we did the first part here. Now this is the first part. Now I want to do like the second part of the whole thing. So I multiply the row vector times the result, which is this one here. And then we can do row times column, and this is the inner product, which gives a single scalar value. So basically, we see that this whole thing here gives us a scalar value only. So it's clear, yeah, that the trace of a scalar value is simply the scalar value itself. So trace, let's say this is the value A, and this is just A. So this is one thing you can see here, but this is basically now the first part. So the scalar value is the same as the trace of a scalar value. And yeah, what you can also show that you can here obtain the same if you do the cyclic permutation. So this way you basically place the last element here is it's a vector, but can treat a vector like as a matrix with only one dimension. And so this rule applies here. So you can take the last element, bring it to the front, and then you have shown the trace trick, which might come handy if you prove some, let's say, relations with matrices. For sure, like in the following lectures towards machine learning, this may show up a lot. But also in other fields, like if you solve differential equations. I come to more motivation later. So let's go to the next concept, which is a norm. So a norm, basically, it's defining something similar to an absolute value for a vector, and it's a function where you plug in an n-dimensional value, and the norm basically just gives you a single scalar, and all the norms have some properties. So the resulting value after you calculate the norm of a vector should be always positive or 0. And the only way it can be 0 should be when the vector you plug in is all 0. And then you have here some further scalar multiplication with a real value of t. So if you multiply a vector times t, then the norm should simply be the same as the name of the vector without a t times t. So either you can calculate first t times the vector and then the norm, or you calculate first the norm of your vector x and then you multiply times t. Here it's important to note that t needs to be always positive. So you take the absolute value here. And there's also something called a triangle inequality, meaning that the norm should follow another rule, namely if you calculate the norm of the addition of two vectors, the norm should be smaller than the norm of the individual vectors itself together. So this all sounds like pretty much math definition. So what does it mean? The most simple thing is the norm simply is the length we know from our space. So if you have a vector, then the norm simply provides you the length. And this type of norm, which is the most intuitive one in mathematics, is categorized as so-called L2 norm, or also named Euclidean norm. And it's simply the length of a vector. And like in 2 dimensions, we can here draw an example. So I don't know if you see my pen, so I use the pointer again. Here you have a vector consisting of two elements, v1 and v2. And now the norm tells you basically the length of this vector. And to do this, yeah, you probably know this. This is like the theorem of Pythagoras. So the square of the one side plus the square of the other is the square of the resulting diagonal line. And this diagonal line, yeah, is basically the length. So that's so far really intuitive. But yeah, sometimes in machine learning, there are like other norms. Often you have like lots of data and you somehow want to boil down it and extract some, let's say, features. And one way to do a feature extracting, if you have a vector and you simply say, okay, my feature of this vector is some kind of norm, and then you pick one of these norms. And one frequent norm is a taxi cab or Manhattan norm. So let's say the most native norm is the length of the vector, which is the L2 norm, which is the diagonal, which is basically now like we think here of New York, and New York has like quite rectangular alignment of streets. So if you take the helicopter, then the distance would be the L2 norm, which is, or if you fly like a bird, then you can take the shorter path, which is like the natural vector length. But if you add up the individual vector components, meaning if you drive a car or walk by foot all along the streets, then the total path you were walking or driving by car is giving you the Manhattan norm. And for example, you can also define something like a maximum norm. So the maximum norm looks at all vector entries and simply picks the longest one. So in this two-dimensional example, the maximum norm would simply say, okay, this street is the longest, so the maximum norm of my vector is x1. Okay, so now you know some norms. There are plenty more. So, and the different norms in mathematics, they can be generalized as like L1, L2, and then LP norm, which is this most general concept of a norm. And also, there's a norm for matrices. So, what is a common norm for matrices? So-called Frobenius norm. And here you need to calculate the transpose of a matrix. Then you do the matrix multiplication of the transpose matrix times another matrix. You calculate the trace, and then you get a scalar value, since the trace gives you a scalar value. So this is like typical for a norm. And due to this trick that you multiply the matrix which itself, you make sure that it's always positive, and then you just take the square of it, and this is then the norm of the matrix. So these concepts appear. One way where a norm is also needed as application, if you set up the most simple form of base vectors, it's nice to have base vectors of length 2. So here you usually take the Euclidean standard norm, which is calculating the length of the vector. And yeah, if you divide the vector by its length, then you normalize the vector and make sure that the resulting length of the vector is 1. So this is like the way to derive a unit vector, is to divide the vector by its L2 norm. Of course, you could also define another way of unit vectors with a different norm, but yeah, this is a common thing to use the L2 norm. So now we come to another operation, which you can do with a matrix. This operation is not always possible. I think so far I only introduce operations which you can do always. So similar to the trace, you need to have a square matrix, or to the determinant, you also need to have a square matrix. And then you can calculate a so-called inverse of the matrices, and this inverse is denoted by this -1. And the inverse is basically, doing the reverse effect of the initial matrix. So if the initial matrix is stretching and rotating something, the inverse matrix is exactly doing the opposite to redo the scratch and to redo the rotation. And the definition of inverse matrix is such a way that if you do first your linear transformation with your matrix, and then you do the inverse transformation, you end up doing nothing. So in case you can find such an A, it always should fulfill this rule that you end up with the identity matrix. And so I hope you remember, I told you before, the identity matrix is doing nothing. So if you multiply an identity matrix to something, nothing happens. And this basically is now stating that the inverse times the original one is doing nothing in the end. And yeah, basically this also should work the other way around. So if you first do the inverse and then the original matrix, you should also end up with doing nothing. So now I want to tell you when you actually have a chance of finding an inverse matrix. You don't know yet how to calculate it, but I just want to tell you like a proof of existence, or actually not the proof, but I just tell you when it exists. Namely, A is invertible if it's non-singular. And now this is now really like a lot of vocabulary you need to memorize. Non-singularity means basically that the determinant is not 0. And as you remember, if the determinant is not 0, then the matrix has full rank, or the matrix has what was the last thing? Yeah, only linearly independent columns or only linearly independent rows. So this linearly independence of rows, which is also called full rank, which is also called non-singular, is the condition to be invertible. Yeah, so there's another way of saying it. If a matrix has full rank, it's invertible. Or if the determinant is unequal to 0, that's it. But yeah, or I could also write down here if all column vectors are linearly independent. So now it all fits kind of together. We need the stuff we defined before. So now I want to show it like some properties of inversion of a matrix. So if you do inversion twice, it's the same as doing the original operation. Then there's another property which is similar to the transpose property. So if you do the inverse of the matrix product, it's not the same as doing the inverse of the individual elements, but you need to flip the order. Maybe you remember this was the same with the transpose. And also, now we can combine inversion and the transpose operation, and actually you can interchange those. So either you can first calculate the inverse and then change column and rows, or you first change column and rows and then do the inverse. So this is interchangeable. And yeah, of course, if you are know calculus well, you know, you have an exponent and another exponent, you can somehow add those together. So a to the exponent of t to the exponent of -1 can be then abbreviated as a to the exponent of -t. So this is just the shortcut for that. Also, we know that the determinant of the inverse is the same as if you calculate the determinant first and then simply invert it. So this is like the cheaper operation, which is preferable because 1 divided over a scalar is cheaper than doing the whole inversion first. How come? I show you now how expensive the inversion is, even for a 2x2 matrix. Not super expensive, but has some complexity. So we start with a matrix A with the entries A, B, C, D. In order to calculate the inverse, we need to calculate the determinant and divide by the determinant. So first we need to calculate the determinant, which is already some effort to do. And then we need to divide by the determinant. And then we also need to do some operations with the matrix itself. So in case of a 2x2 matrix, it can be simply written down by you flip the order of the diagonal elements, like it's done here, and you add a minus sign to all elements which are not on the diagonal. But yeah, this is just like a cookbook rule. This can be generalized with a way more complex formula. And of course, there are great algorithms to do it. Those algorithms, usually start with the basic definition of an inverse, such that, let me think, pen. But again, the main point is, it's good to understand that the inverse is basically like the counter operation, but the actual calculation of the inverse then is best done with a program. So mainly, like what was the definition? A minus 1 times A is the identity matrix. And then there are some algorithms which write out all these entries here. So basically these are the entries the algorithm is looking for. Then these are the entries of matrix we know. A, B, C, D. And this should give the identity matrix. So 1, 1, 0, 0. And then, you have here unknowns. And then you do the matrix multiplications. Then you have like a set of equations with unknowns here. For unknowns, let's say those 4 questionnaires are 1, 2, x4. Those are unknowns. And they are somehow equal to this right-hand side. So this way you have a linear equation system, and then there are some tricks to calculate it. So I think it's not important to go into too much details, since we want to also come to the eigenvectors today. For a block diagonal matrix, the inversion can be obtained by inverting the diagonal matrix blocks individually. So in case you have a big matrix consisting of smaller 2x2 matrices, A and B, then you know how to invert the 2x2 matrices, and then the inversion is more simple. So if you have a more sparse shape, so meaning a lot of zeros and mainly diagonal elements, then the inversion also stays inside those diagonal elements or neighboring diagonal entries only. Okay. You can also have like orthogonal matrices and vectors. I was giving you the definition of a orthogonal vector before. So the dot product is the scalar, and this scalar should be 0. And then you're sure the vectors are orthogonal. This can be interpreted like you have a 90 degrees angle between two vectors. So in order to have an orthogonal matrices, you also demand that the vectors building up this matrix are normalized. So, and here you typically demand a L2 norm, so that the lengths of the vectors are 1. And then you can use these orthogonal and normalized vectors, which are orthonormal vectors, to set up an orthogonal matrix. So often if you're talking about orthogonal matrices, you imply that they are also normalized. This is slightly different to vectors. If you have two orthogonal vectors, they do not necessarily need to be normalized. Of course, it's nice if they are, but let's say for vectors, this is independent. But typically, if you are talking about an orthogonal matrix, you're also meaning that the vectors are not only orthogonal to each other, which creating these matrices, but they are also normalized. So orthogonal matrices implies normalization. Here, I just show you that such an orthogonal matrix, if you transpose it, it's similar to the inverse transformation. So the transpose operation on an orthogonal matrix acts as reversing the effect of the first matrix. So yeah, it's the orthogonal matrices are really easy to invert, let's say. And if you transpose an orthogonal matrix, you always have like the counterpart to redo the action of your initial matrix, and you end up with doing nothing, which is the identity matrix. So this is like a nice property of orthogonal matrices, that they are easily working as inverse matrices as well. And yeah, what we can do now to prove those two properties. So we set up a matrix, and now we need to make sure that the three vectors U1, U2, and U3 are all orthogonal and are all normalized. And then we build our orthogonal matrices by the outer product of our two vectors. And no, not by the outer product, sorry. These are two matrices we multiply together. And one time we have the transpose matrix, and one time we have the matrix and just consisting of the row of the column vectors U1, U2, U3. And so it's a matrix multiplication. So we apply the rules of matrix multiplication. We take the first row U1 times the first column U1, which ends up with being a scalar product, which gives us the first entry of the resulting matrix. And then we can continue this system. So for example, for this entry here, we take the second row of the first matrix times the first column vector U2 of the second matrix. And then we end up, yeah, now I was picking the second and the second, so we end up with the central element here. And now if we look at those elements, we know that they are normalized, meaning if you multiply two normalized vectors, then their length is still 1. And also they are orthogonal, meaning if you multiply two vectors which are orthogonal, then the scalar product should be 0. So all these elements here, beside the diagonal, they end up being 0, and only the diagonal elements end up being 1, thanks to normalization. And hence, we've shown that, yeah, if you pick vectors which have these two properties, you end up with a orthogonal matrix C. And if you multiply like the inverse of the orthogonal matrix C times the orthogonal matrix C itself, which is done here. So maybe I can also make this clear. My pen again. So this is basically the transpose matrix, and this guy here is the original matrix. So this way we have proven, if we build up our orthogonal matrix out of these vectors with these properties, then they are indeed ending up with the identity matrix. And yeah, what I told you already before, since the inverse is defined as A inverse times A is equal to the identity matrix, we know from comparing these both two that for orthogonal matrix, the transpose operation is equivalent to the inverse operation, meaning for those matrices, it's, yeah, they are most easy to invert. Okay. There are some properties, I just mentioned them shortly. So if you apply an orthogonal matrix on a vector and then calculate the norm of the resulting vector, it's the same as calculating the norm directly of the vector. So I think that's not important to go into detail now, but you could also show it yourself. I want to come to eigenvectors and eigenvalues now, which is the next big topic. So I'm glad we made it. So let me look at the time. So I think it's great. We have 40 minutes, 45 minutes left. Eigenvectors and eigenvalues are somehow some intrinsic properties of a matrix. Eigen is in Germany something like self or own or like intrinsic. Yeah, I give you now simply the definition, and then we start to interpret this. So if we have a square matrix A, this again is now a restriction to a square matrix, then we say that lambda is an eigenvalue of A, and X is an eigenvector of A if they hold to this relation. So now you already know that in most general case, those eigenvalues and eigenvectors can be complex, even though your initial matrix is real. Today we will stick only to matrices with real eigenvalues for this part of the workshop. But yeah, in generally you need to know that to find really all possible eigenvalues and eigenvectors of a matrix, you need to extend the number plane to the complex number. otherwise you won't find all eigenvalues. And sometimes it's even not possible using complex numbers. Sometimes it's, there are no eigenvalues. But yeah, now we focus on the real eigenvalues and real eigenvectors, even though they possibly could be more. And what is this basically telling you is, this is a matrix, this is a vector, this is a, I switch to the laser pointer. This is a scalar, so the eigenvalue is always a scalar, and the eigenvector is always a vector. And if you usually if you apply a matrix to a vector, then you end up getting a totally different vector, which is not linearly dependent on the input vector. But the eigenvectors, they are basically or the result of this matrix operation is basically another vector which is linearly dependent, or we could say it other ways, another vector times a scalar, and this scalar is the eigenvalue as the result of this vector operation. So this is like a subset, only a subset of all possible vectors you can apply to a matrix C, is having this nice property that the vector again is the result of that calculation with some prefactor lambda, and this prefactor lambda we call eigenvalue. And we exclude the trivial solution. So of course you could define a zero eigenvector and a zero eigenvalue, and then this holds true. So let's say every matrix has a zero eigenvalue and a zero eigenvector. And so there's always this trivial case, but we are now want to look for more non-zero solutions of these equations. And we can do this as follows. So we write down here our definition. So A times our vector x gives the eigenvalue times the vector x, which is the eigen. The vector x is the eigenvector. And then we know that the neutral operation, or the operation which is doing nothing, is the identity matrix holding ones on the diagonal. So we simply can add up here an identity matrix in front of our vector, and we change nothing. Now we can subtract the whole right-hand side and put the right-hand side of this equation to the left side. So here you see now again the eigenvector, our identity matrix, and then we use some brackets because both A and lambda times I is acting on our vector x. So since they're both acting, we know that we can, according to the properties of our vector space, we can simply factor out the x here. Now we have like a modified matrix. So the modified matrix has the unknown, which is our eigenvalue, the scalar lambda. And this lambda value now lives on all diagonal elements. And we subtract lambda basically from all diagonal elements of A. So now we can look at when this is true. So we want to make sure that our matrix times the vector gives actually 0. And in case this whole thing here, the whole bracket content, A minus lambda I, if the resulting thing inside the brackets has full rank, then it's not possible to multiply it with any value and get 0. Of course, we exclude the 0 vector. So maybe you can think of like the standard base where we have like yeah, maybe I write it down. So, okay, we have standard case 1, 0, 0, 1, 0, 1, 0, and 0, 0, 1. So now this is like a most simple case of the matrix with full rank. Then now you multiply all these columns with some prefactor. And if that with this vector x, so vector x should give 0, meaning basically now we can write x in its components. So vector x has 3 components we are looking for. And we exclude the trivial solution. And as soon as one of these entries of our vector is not 0, you never end up at 0 here. So yeah, this is just for the natural base. And generally, you would need to show this also for arbitrary basis. But yeah, just to give you an idea, it's not possible to find a linear combination which ends up being 0 if those are linearly dependent. And one way to ensure that there's at least one linearly independent, so in this case, they're linearly dependent and you never can find a 0. But in case we can make one of these entries here linearly dependent, then we actually can arrive at 0 with a non-trivial eigenvalue. And yeah, the determinant is exactly now this way to ensure this. So we know if the determinant is 0, then we know that they are linearly dependent. And if they are linearly dependent, then we have the chance to create a 0 vector. Namely, for example, we can do now a really simple example. Let's say we have the vectors 1, 0, 0, and 1, 0, 1, 1, and 1, 2, 0. So now the second and third column vectors are linearly dependent. And now if we, for example, pick our eigenvector would be to be -2, 1, then we can again do our matrix multiplication. So row times column. So 1 times -2 and 2 times 1. Then we actually found the possibility to end up being 0. So the determinant now is really powerful to tell us or to ensure linearly dependence. And if they're linearly dependent, then we actually can achieve a 0 here. Also in the video where the determinant was visualized, here in the interpretation, the determinant gives the volume which is created by the parallelepiped, or simple by the space between two vectors. And if two vectors are linearly dependent, they're parallel, and then they have 0 space. For example, in 3 dimensions, you can also imagine this, that if one vector is determined on linearly dependent on the 2 others, then it lies within the same plane, or the determinant will tell us in this case that the volume of a plane in 3 dimensions is 0. So whenever the determinant is 0, this means that the linear transformation is reducing the dimension. And if you reduce the dimension, you end always up with a volume which is 0. So if you are in 2 dimensions and you reduce the dimension to 1, then the area in 2 dimensions is 0. Or if you are in 3 dimensions and you reduce a volume to a surface, then the volume in 3 dimensions is 0, because the surface in 3 dimensions has 0 volume. So yeah, long story short, basically you can apply this as the cookbook. So the determinant tells you that actually it's possible to create a 0 vector here. And we are looking only for those eigenvalues which end up solving this statement here, being here a 0. So only those lambdas which have a determinant equal to 0 are the ones we're interested in, since they solve this equation. So we can now simply apply the rules how to calculate the determinant. I would do this on an example in the next slide, but for now I'm simply telling you, yeah, you end up that the determinant is a scalar value, meaning you have some scalar, that you have a big equations where the lambda is inside, and you need to solve it for lambda. And yeah, in the easy case, lambda will be a real scalar number, and then you can plug in your eigenvalue back into the equation here. So I switch to the laser pointer. So if we found one eigenvalue which is solving this equation, we plug it back into this line here, and which is written down at the bottom of the slide. So you plug in one concrete eigenvalue. You know that this eigenvalue fulfills this equation, and now you're looking for a corresponding eigenvector, which makes the whole thing finally be an eigensystem consisting of an eigenvector with its corresponding eigenvalue. So let's do it. First I summarize. So we have the definition of eigenvectors and eigenvalues, and the definition is that the eigenvectors, they don't change under the impact of the matrix multiplication, but they stay the same. The only difference of the resulting vector is that there is a scalar multiplied in front, and this scalar is an eigenvalue. In order to calculate the eigenvalues, the only possibility is that the determinant of this expression here is 0. And you can solve this equation here for the lambdas. And then you can set up actually a whole eigensystem of eigenvectors. So this capital X basically is just is a matrix containing all the eigenvectors. And this lambda matrix here is a diagonal matrix, and this diagonal matrix is containing all the eigenvalues. So in case you find several pairs, usually there are always pairs of eigenvalues and their corresponding eigenvectors, then you can add up all your pairs you found in such an eigensystem. I want to show you some geometric interpretation now. Here on the right-hand side, you see let's say the dot where a vector is ending, and then this dot is moving due to the fact that the vector is linearly transformed by our matrix A. And if we have a vector which is lying on the line of all the eigenvectors. So in this example here, we have one eigenvector, which is this red line here. So let's say this eigenvector is normalized and has, or for now, yeah, it's, let's assume it's not normalized, then it's maybe easier to write down. I do it here. Pen again. So we have here, for example, this guy most likely is an eigenvector of the shape. Maybe 2 in the direction of x and 1 in the direction of y. So this is not normalized yet. So we need to normalize it. So I simply now divide this by the square of 4 plus 1. So this is now the norm, this is now the length of the vector in the 2 norm. So, but what I wanted to say, of course, here it's an infinite long line, but the eigenvector points in the direction of this red line, and the second vector here in this example points into this direction. And this is now the second eigenvector. This was the first one. And now if you plug in some value, so the blue dots here corresponds to, so this x here are the blue dots of this visualization. They are transformed, and like, let's say arbitrary, they're stretched and rotated somehow. But the one vectors we plug in, which are lying exactly on this line here, they are just stretched or scaled down along the line. So you see that a point on this line is never leaving the line, while you could draw no other line in here where the points stay on the line. So this property that the vector, the eigenvector, is unchanged under this linear transformation means it's an eigenvector, and it means that it always stays on the line after transformation, and it's only changing by a value of lambda, which is moving it further or closer to the center, but always along the line. Okay. So let's do it. Here's an example. We have here some matrix given. The matrix has the entries 1, 2, 0, -1. And we calculate now the determinant of this matrix minus the diagonal matrices with lambdas. So as a reminder, to calculate the eigenvalues, we first need to subtract a diagonal matrix with the lambdas, and then we need to make sure that those are zeros. Otherwise, we can never, and those are no eigenvalues. And so we subtract the diagonal entries lambda here. Then we calculate the determinants. So I do it here all at once. So 1 minus lambda times -1 minus lambda is the diagonal. So that's the first row here. Oh, let me check. I'll jump back to the laser pointer. yeah, 1 minus lambda is the first entry, and to calculate the determinant, we need to calculate this by -1 minus lambda, which is the lower right part, or the two lower right entries. And yeah, on the counter diagonal elements, or elements beside the diagonal, there's 0, so this gives us nothing, so we only stay with the diagonal part here. And if we look at this equation here, we already see that to solve this, one lambda can be 1, and the other lambda can be -1, and then we found a solution of that system. Of course, I picked it in a way that this is like an even number. This could be like an arbitrary complex number. Now we found the eigenvalues. Now we are looking for the first eigenvector corresponding to the first eigenvalue. So usually you always find at least one eigenvector per eigenvalue. There are also cases where you can find more than one eigenvector per eigenvalue, but yeah, this is not covered now in this workshop. Just that you are not surprised if this happens in the future. So we plug in now our eigenvalue in our original equation. So maybe we jump one slide back. So we plug this eigenvalue in, and now we solve for the eigenvector x corresponding to our eigenvalue. So the eigenvector is subtracted, -1, -1. And then we're looking for our eigenvector v1. And yeah, we want to make sure that this is 0. Actually, I should add this here, otherwise it doesn't make too much sense. So let me give me a pen again. So this should be 0. This is what we are looking for. Here. Oh, sorry. So I subtracted the eigenvalues, end up with this matrix C, 0, 0, 2, -2. Now we look for entries of our eigenvectors which make this come true, namely equal to 0. And this can be done with any scalar value in the first component, because there are zeros here in the both first and the first column only has row zeros, and to make it 0, the second column should be 0. Otherwise, we don't end up with a 0 vector. And the forbidden solution is a trivial solution, the 0 vector. So instead of picking a 0 here, we want to pick some useful value. So there's always a lot of freedom while defining eigenvectors. But usually you pick the values in such a manner that they are normalized. So you could pick anyone like a 3. This would also solve this equation to 0. But yeah, often then for later steps, if you want to work with eigenvectors, it's nice to have also the normal, it's nice to have them normalized. And then a natural choice would be to pick a 1, because then the vector is normalized to the length of 1 in the L2 norm. And then we can check whether this is actually an eigenvector simply by plugging it back into the original equation. So if we look at our original matrix C and we multiply 1, 0 by our matrix C, we are getting for the first entry here. So let me do this for the first eigenvector explicitly here. So we assume that this is a proper eigenvector, so we do matrix multiplication one more time, and we find, hooray, that the result of the multiplication is still the same vector. Actually, it would be okay if the vector has had another value like a 2, as long, no, in this case not, and this would require a determinant of an eigenvalue of 1/2, because the eigenvalue times the vector should be the same as before. So since we have the eigenvector of 1, the eigenvalue of 1 is should be I erased all. So 1 times 0 was the eigenvector, and yeah, it really needs to be the same, because we want to make sure that our matrix times the eigenvector, which is the definition of eigenvectors and eigenvalues, is the eigenvalue times the eigenvector. And since our eigenvalue is 1 for the first eigenvector, the both eigenvector needs to be exactly the same. So now we calculate the second eigenvector. So again, we plug in our second eigenvalue, which is -1. We need to subtract the eigenvalues. So -1 minus is again a plus. So we end up with a matrix 2, 0, 2, 0. And now we are looking again for some eigenvector, which is solving this to 0, as before. And here again, you have some freedom. The one way to do it is to pick an arbitrary value here, and minus the same value at the second entry. So 2a minus 2a gives 0. And of course, we don't want to have the trivial solution. And at best, we want to have some easy looking results. So here I pick 1 minus 1. So this is actually a valid eigenvector. This is not normalized though. So to normalize it, we need to divide it by square root of 2. But yeah, in order to show the eigenvalue properties, normalization is just a bonus. So, and if we plug in now this value, so let me find the proper eraser. So I just want to delete this. And then where's our pen? Somewhere down the menu. So now we have we found our second eigenvector. Actually, this is the second eigenvector. I hope no one is sleeping since you didn't comment on that. So this is the second eigenvector, which we try out now. And the second eigenvector is again matrix multiplied. And we find here a -1. And here -1 times -1 is 1. So this is exactly the same eigenvector as before, a part of the switch sign, and this sign comes to the fact that the eigenvalue has minus here. So again, we can write down the equation, which is true, that the second eigenvalue times second eigenvector, second eigenvalue times the second vector is the same as the vector matrix multiplication before. Okay, cool. And now I just want to do the last step, like to set up an eigenbasis out of these eigenvectors. These eigenbases, yeah, it's useful. And then in later context, I'll tell you in a second why. Give me my laser pointer back. Here we go. So we found our vectors 1, 0 and 1, -1. And now we can simply, oh, well, not simply, but we also, again, apply the rules to calculate the inverse of our eigensystem. As a training, this is good. So we can calculate the determinant. So I just plug in the definition here. The determinant of our matrix is -1. And then we need somehow to flip A and D. So the upper left and lower right element in a 2x2 matrix needs to be flipped and to calculate the determinant, and all elements which are not on the diagonal need to get a minus sign. So this operation here I just wrote down is basically the definition to calculate the inverse in 2 dimensions. And yeah, since the determinant is -1, we flip the sign of all this here and arrive at this inverted eigenbasis. And we can again check this that our inversion was successfully. So if we multiply the original eigenbasis times the inverted one, this I leave for you. So if you're bored, you can do it on your own. And you find that the identity matrix is showing up. And yeah, but I just wanted to make sure that at least once you saw the whole cookbook, how to work with eigenvectors, eigenvalues, and to set up a base. And now you can do something, let's say, yeah, nice to the original matrix. Namely, you can do a so-called basis transformation. So this eigenbasis of eigenvectors can be used to transform the original matrix in a manner that it's more simple than before. What I mean by more simple follows in a sec, but first we stupidly do it. So we have the inverted eigenbasis, we have the matrix, and we have the normal eigenbasis. First we do the first matrix multiplication. I hope you by now can do matrix multiplication. First element comes from first row times first column of second matrix. So the first two matrices here give me this matrix, and we still need to multiply by the third matrix here. And then we fully transformed our original matrix A. So we plug in the matrix X here. We do another matrix multiplication, and we're ending up with a matrix 1, 0, 1, -1. And this matrix actually has a diagonal shape, and the diagonal entries are the eigenvalues of our original matrix. So basically, yeah, we could have ignored all of these operations and directly write down the fact that we can use our eigenbasis to transform our matrix to, let's say, another space. And in this space, the matrices has only diagonal entries. So if we look back at this slide, this is basically yeah, meaning the same. So we could like multiply this matrix on both sides with, write it down, could add on both sides the inverse matrix, and then we end up with the inverse matrix times X. Here we have the inverse matrix times the matrix times X times A. So we know that the inverse matrix is basically doing the counter operation, resulting in an identity which does nothing. So this equation, X inverted AX is equal to A, is equal to so on this side, this is not an A, but a lambda. This doesn't make sense. So X is equal to X lambda. And then we can add like our inverse operation on both sides. So I was writing down the wrong matrix on the right-hand side. We see that this is the identity matrix, which is giving us the lambda matrix, which is holding the diagonal entries. So basically, yeah, this compact writing of all eigenvalues and eigenvectors together is exactly what we just did here. So why this is nice, why would people do all these calculations to transform a matrix? This matrix system is better than that one. This is a coupled matrix system, meaning if you have like some equations, you need to do more operations, obviously, because there are more entries which are non-zero. In this form, you always have zeros all over the places. Only on the diagonal, you don't have, you have elements. So you see already working with this, you do simpler operations, which are faster. And by coupled, I mean, if you work with this matrix C, and you multiply a vector, then the first entry of the resulting vector is actually the sum of both vector parts, meaning that two different dimensions of the vector are needed in order to calculate the resulting first dimension. So you need multiple things in order to calculate one. Of course, if you have a strict diagonal matrix C, then the entry in the first dimension always stays in the first dimension, and the entry in the second dimension stays in the second dimension. And there is not this coupling of dimensions, or the different entry of a vector end up in another place together. This is now avoided, which makes calculations way more easy. And actually, there are many techniques, so-called, now this is a big outlook. If you're going to work with differential equations, differential equation systems, or even partial nonlinear equation systems, you somehow find a form where you can like decouple the system, and you have an equation system which can be reformulated in a way that all the matrix multiplication is this simple diagonal entries. And there are like, let's say, cookbook recipes how to solve coupled equation systems based on this principle. So you need to first find this form, and when you have this form, then based on this form you can state a solution of your linear equation, meaning you do not need to solve the equation system anymore. You directly can calculate the result. And another thing, maybe in machine learning, and now this is like now still some jump to something like a principal component analysis. But those are like characteristic features of the systems. And if you have lots of data, let's say a full matrix with complex things going on, and you want to boil down the whole data, you measure it to some single values which actually are most dominant in the system, then yeah, this way of finding a diagonal matrix is actually the same idea of a principal component analysis. Also there, you basically transform your matrix system and you end up with a matrix which has like only diagonal elements. And this way, you could also, for example, then order those elements regarding, you could order also the eigenvalues here with decreasing length, or not length, it's a scalar value only with decreasing value. And then often, for example, the assumption is true that if you have a complex system, you can describe it more easily if you just take like the dominant parts of your eigenvalues, or the dominant components or the largest components inside the diagonal. And if you have like a huge system, this diagonal matrix will have many entries. And for example, one approximation of your system could be that you skip all eigenvalues which are super small, since you're saying those are not important to describe my system dynamics. So yeah, this is a way like to figure where's the golden needle in all the mess of big equation systems. So that's for this. I want to just give you some last properties of eigenvectors. So the trace of a matrix is actually the same as if you calculate the sum of all eigenvalues. And the determinant of a matrix is actually the same if you calculate the product of all eigenvalues. So you already see that the eigenvalues hold a lot of information about your systems in one value. And yeah, this is helpful to extract features, for example. And also, like if A is non-singular, so you can invert your matrix system, then applying the inverted system to a matrix, to a vector X, is the same as if you know the eigenvector. So no, you cannot apply the matrix, the inverted matrix, to an arbitrary vector. This here only applies for eigenvectors. So if you apply an inverted matrix to a eigenvector, then this is the same as if you multiply the eigenvector by or if you divide actually the eigenvector by its eigenvalue. Okay, and the eigenvalues of a diagonal matrix are just the diagonal entries. Okay, that's what I just said before. And now I want to give you some more motivation for why this could be useful for my PhD. So during my PhD, I was investigating basically like flow into boxes. So there's an upper box, and there is like a flow in this box, and on the wall or bottom surface of this upper box, the flow is like slowed down because the surface is of course stopping the fluid flow, and due to the slowdown, there's like a shear process, and this shear process ends up in vortices. So basically, like if you blow over a surface, then there is like near the surface, there are many small vortices. And here you see the pressure value of the fluid. So actually, if you have a vortice, depending on the rotation direction of the vortice, either in a vortice, or actually a vortice is the same as a whirl. Maybe a whirl is more convenient to you. Well, it's the same. A whirl or vortice has then a negative or positive pressure core. So I just want to point out that here it's pressure, and for example, here are many pressure cores which are negative, meaning here are vortices spinning in clockwise direction, and the red one here, for example, is a vortices spinning counterclockwise. So, so here are a lot of vortices, and in the bottom chamber, there are also here some vortices, but pressure can not only describe vortices, pressure can also describe acoustics. So, and below my, let's say, flat plane with flow, there's a box so this, the upper box is actually open. So here the flow comes in, maybe I can write it down. Here the flow comes in, and here the flow can leave. But here there are solid walls in this lower box. So here the flow cannot exit. And if you have like, for example, if you have a beer bottle and if you blow on top of the beer bottle, you can hear a sound. And similar, if you have like a pan flute or flute in general, then you have like a vibrating chamber, and you blow on top, and inside the chamber there's some acoustic vibrations appearing, and there are acoustic waves traveling up and forth in this box. And yeah, well, this is what you can see here. You can also read the thesis if you want. Well, it's not so important for understanding linear algebra, but I just want to show you. So let's assume you have data. So you did a simulation, and now you see here, well, there's something going on, but yeah, it's hard to interpret these data and to know what to do to write a nice analysis of this data. And what you can do then, or maybe we watch this to the end. You can do, for example, snapshots of your data, and this is what I also did in my thesis. So you capture all the pressure values in this domain, you capture all velocities and densities, and then yeah, you somehow know how to calculate the matrix C, which is telling you if you have an old vector in time, how if you can describe one time step, how the matrix then tells you how the next time step will look like. So if you apply the matrix C, then you find how the next time step will look like. So now we can do something like a linear stability analysis. This implies that the distance between corresponding time steps is really, really slow. Again, it's really, really small. So if the time steps are too huge, this is no linear transformation anymore, because there's more than just rotating, shearing, and so on. But if we do like a tiny time step, then actually we can find a linear matrix, which is like combining two states in time. And then we can do now the whole mechanism of determining the eigenvalues and the eigenvectors of our matrices. And these eigenvectors then, regarding on the context of the data you're looking at, have some system-specific meaning. And in this case, the imaginary part of the eigenvalues will tell you the frequency of something. So, and the corresponding eigenvector is something like a system mode. So I want to show this now. The modes, or the fundamental modes of the system, are not too complex. They are basically like, if we look at acoustics, the basic mode 0, 0 means everything has the same value, so everything is red here. And the first eigenvector now is a mode which has a positive upper part and a negative lower part. And the next mode, for example, this would be in vertical direction. The next mode could be in X direction or in horizontal direction, has positive sign at high values and small sign at lower values. And higher modes have this chess pattern. So basically all the complex structures here can be transformed to a basis of modes which are like easy. You can also think of it maybe of a, if you know, like a Fourier transformation, but yeah, no, maybe that's a bad example. But basically you have elementary parts of your system. And what is nice now, that, for example, the eigenfrequency, which is just the real part, the imaginary part of the eigenvector. So the complex, if you have complex eigenvectors, the imaginary part of that gives you the frequency, tells you that you have an acoustic frequency, let's say, 4,000 hertz, and the 4,000 hertz frequency is actually vibrating with this pattern. And then you have another acoustic frequency, which is vibrating and creating this pattern. So you get like an understanding which patterns in space, which are the eigenvectors, vibrating with a certain frequency. And also, here I highlight the top part, which is like the neck opening of my, like the connection of the upper flow and the lower chamber. In this connection region, there are like plenty of vortices, and some vortices, and these vortices are also like seen in the eigenvectors as spatial distribution of pressure here. And those are also vibrating at the same frequency, since this is also the eigenvector corresponding to the same eigenvalue as the lower part. So actually here you can see you have a vortice. So of course you need to know that vortices have this pressure maxima and minima interpretation. But if you know this, then you can somehow see that acoustic vortices are coupled to certain acoustic frequencies, so that a certain pattern of vortices in the neck or in the coupling region of the upper and lower box here, that a certain pattern of vortices actually is coupled strongly to a certain acoustic frequency. And this way you can start interpreting systems. For example, another application would be if you have brakes in a car, you could also like analyze the screech pattern. So if your brake pads create a certain mode on your brake pad in the car, then you can calculate the corresponding screech sound and whether the screech sound of your brakes is annoying with the human hearing. So yeah, this is just to make one application of the complex topic of eigenvalues and eigenvectors. So with this, I want to finish. So thanks so much for attending. I hope this was nice. So you can still post questions to the chat. I will be there for a few more minutes and answer those. And again, I have one final video. So that is 10 minutes. So yeah, I think if you want to ask something right now, I answer the question. Otherwise, I would just show you the final video with some visualization of the eigenvectors and eigenvalues. So in case you're watching on YouTube again, you can simply Google it. And we will also post the link here, which is shown on the top in our final printed slides. Then we are safe. So then all have a great weekend together. I think there are no more questions in the chat. So yeah, enjoy the summer school. Bye from my side.
Thank you so much, Lewin. That was amazing. Thank you, everyone, for participating.